you can see clearly here, I have already shown you. Here you can see clearly here at higher loads. At higher loads, so this is the graph with respect to torque and armature current for different types of motors. This is the graph for DC series motor, and this is for the DC shunt motor, and this is for the DC compound cumulative motor, and this is for the differential DC motor. So you can see clearly, see at higher loads means IA is higher, you can see clearly this cumulative compound motor is having high torque when compared to shunt motor. So this is what I am trying to tell here. So this cumulative compound motor is having the more torque when compared to, so we can say that here, you can simply see here at huge amount of IA current, whatever the torque of the compound motor is higher when compared to shunt motor. So we can say simply at higher loads, a cumulative compound DC motor has high torque than a shunt motor, as you can see clearly from the graph itself. So therefore, at higher loads, a cumulative compound DC motor has high torque than a shunt motor. This is for the series motor, this is for the compound DC motor, and this is for the shunt motor, and this is for the differentiable DC motor. So at higher loads, then it means that IA is very higher. So a cumulative compound DC motor has the high torque than a shunt motor. The primary ampere turns are equal to the secondary ampere turns in a transformer, which means that the MMF is always balanced. So whatever the primary ampere turn is equal to the secondary ampere turns, means simply we can say N1 I1 is equal to N2 I2. So therefore simply we can say the primary ampere turns are always equal to the secondary ampere turns in a transformer. Simply we can say that the primary MMF is equal to secondary MMF, means the primary ampere turns are equal to the secondary ampere turns in a transformer. The flux in the iron core remains the same for no load and full load conditions in a transformer. I have already told you the flux in iron core remains the same irrespective from no load to full load conditions in a transformer. Whether you go from no load to full load conditions, whatever the flux in a transformer is always constant. The flux in the iron core remains the same from no load to full load conditions in a transformer. So in a transformer, whatever the flux in the core is always constant from no load to full load. When two single phase transformers are operating in parallel, the transformer having the greater leakage impedance means greater leakage flux shares less load. So when two single phase transformers are operating in parallel, the transformer having the greater leakage impedance means greater leakage flux shares less load. This is a very important point. It is inversely proportional. So when two single phase transformers are operating in parallel, the transformer having the greater leakage impedance means we can say that greater leakage impedance means greater leakage flux will share the less load. So it is inversely proportional. More is the leakage impedance, less it is going to get sure, because it is inversely proportional. So when two single phase transformers are operating in parallel, the transformer having the greater leakage impedance means greater leakage flux shares the less load, because both are inversely proportional. So more is the leakage impedance, it will share the less load. Less is the leakage impedance means it will share the more load, because both are inversely proportional. So losses are of three types in a DC machine. They are iron or core losses, or copper loss, or ohmic losses, or mechanical losses. So these are the losses which are going to present in a DC machine: iron loss or core loss, copper loss or ohmic loss, or mechanical losses. So these are the three types of losses that are going to occur in a DC machine: iron loss or core loss, second one is ohmic loss or copper loss, and the last one is the mechanical losses. So these are the three types of losses that are going to occur in a DC machine. First one is called as iron loss or core loss, second one is the copper or ohmic losses, and third one is the mechanical losses. Always input is equal to output plus losses, because whatever the input toward should go to output and also in the losses. So input is always equal to output plus losses. Iron loss is the combination of the eddy current losses plus hysteresis losses. I have already told this important point. So iron loss is the combination of the eddy current losses plus hysteresis losses. I have already told you eddy current loss is directly proportional to Bm square F square into T square, and the hysteresis loss is directly proportional to Bm to the power of 1.6 into F into volume of the core. Volume voltage induced inside is always AC. So WE and WH still present in a DC machine. I have already told you, suppose in a DC machine, basically in the winding, the armature winding will have always AC current. So whenever there is a AC, frequency is also associated. So therefore we are going to get the eddy current loss and also hysteresis losses. So voltage induced inside is always AC. So iron loss and the hysteresis loss are going to be present in a DC machine, because still inside the armature coil there is a AC nature. So AC nature means definitely there will be a frequency. So then we are going to get the eddy current loss also and the hysteresis loss in the DC machine. See, iron loss and hysteresis loss present only when the machine is rotating. As N increases, then W and WH increases because inside DC machine frequency and voltage increases. So therefore voltage and current increases. So simply what I am trying to say is basically this WE and WH present only when machine is rotating. Means whenever the machine is rotating, then only the current is going to generate in the winding, then we are going to get the losses. If we are not rotating, means there is no current. If there is no current, definitely there is no iron and the eddy current and hysteresis losses. So therefore, hysteresis and eddy current losses are going to present only whenever the machine is rotating, because whenever the machine is rotating, current is going to induced in the armature. So therefore, simply we are going to get then the iron and then only the eddy current loss and the hysteresis loss are going to get occur. So if the speed is equal to 0, there is no hysteresis and eddy current losses in a DC machine. So therefore, as N increases, then both the iron and hysteresis loss are also increases. So iron and hysteresis loss increases because inside DC machine frequency and voltage and current also increases. So in a DC machine, if the frequency increases, if you go for the, suppose if you increase the speed, if you increase the frequency, if you increase the speed, definitely the frequency of current is also increases. Again, the hysteresis and the eddy current loss will increase. So finally what I am trying to say is, whenever the speed is equal to 0, eddy current loss and the hysteresis loss are 0 in the rotating machine. If the speed is increases, then definitely current is also, the current frequency increases in the armature winding. So therefore, the hysteresis and the eddy current loss are also increases. DC machine armature is made up of silicon steel. I have already told you, DC machine armature core is made up of silicon steel. These things I have already told in a very detailed manner. See, in a DC machine, see basically yoke is non-laminated, poles are laminated, and the armature core is also laminated. And the armature core is laminated because to reduce the eddy current losses, and it is made up of, in a DC machine, armature core is made up of silicon steel. I have already told you, because silicon steel laminations are used for the armature, because I have already told you yoke is non-laminated, poles are laminated, and the armature core is also laminated with the help of silicon steel laminations. In order to find iron loss, operate machine at rated voltage. In order to find copper loss, operate machine at rated current. I have already told this important point. If you want to find the iron loss, you have to operate the machine at rated voltage. If you want to find the copper loss, then operate the machine at the rated current. These things I have already told you. If you want to find the iron loss, just operate the machine at rated voltage. If you want to find the copper loss, just operate the machine at rated current. So in order to find the iron loss, operate machine at rated voltage, and in order to find the copper losses, operate the machine at the rated current. So therefore, if you want to figure out the iron losses, just operate the machine at rated voltage. If you want to figure out the copper losses, then operate the machine at the rated current. Mechanical losses are of two types, which is called as the friction, which is brush bearings losses, and it is proportional to square of the speed, and the windage losses. So mechanical losses are of two types, which are called as the friction, like brush and bearings losses, and it is proportional to square of the speed, and the windage losses. So therefore, simply mechanical loss is the combination of the friction losses plus windage losses, or simply we can say mechanical loss is a combination of the friction losses and the windage losses. So mechanical loss is also called as the friction and windage losses. So mechanical loss is also called as the friction and windage losses, because mechanical loss is the combination of the friction losses and also the windage losses. So therefore, simply we can say the mechanical loss is the combination of the friction and the windage losses. So therefore, simply we can call it as the mechanical loss is the combination of the friction and windage losses. So now the rotational losses means it is a combination of the iron loss plus mechanical losses. The rotational loss is also called as the stray losses. So rotational losses means it is a combination of the iron losses plus mechanical losses. So the rotational losses means it is a combination of the iron losses plus mechanical losses, and mechanical losses means it is a combination of friction and windage losses. So mechanical loss is also called as the friction and windage losses. So the rotational losses means it is a combination of the iron loss plus mechanical losses. The rotational loss is also called as the stray losses. Losses present only when the armature core rotates. See, whenever the armature core rotates, then only the rotational losses are going to present. If it is not rotating, means definitely there is no rotational losses. So rotational losses are going to occur only when the armature core rotates. If it is not rotates, means the armature losses are 0. So finally we can see that the total losses means it is the combination of the rotational losses plus copper losses. See, I have already told you rotational losses is also called as the stray losses. It is a combination of the iron loss plus mechanical losses, plus the copper loss. So therefore the total loss is nothing but it is the combination of the iron loss, copper loss and also mechanical loss. So listen carefully. Total loss is nothing but it is a combination of the iron loss, mechanical loss and the copper loss. So iron loss plus mechanical loss is called as the rotational losses plus copper losses. So finally we can say that the total losses are nothing but iron losses, copper losses and the mechanical losses. But iron loss plus mechanical loss is called as the rotational losses. So rotational losses plus copper loss is nothing but total loss. Or simply we can also call as the constant losses plus variable losses. So this is a very important point that you always have to remember. See, the total losses in a DC machine is equal to iron loss plus copper loss plus rotational loss plus mechanical losses. So listen carefully. The total losses in a DC machine is equal to iron loss plus copper loss plus mechanical losses. But iron loss plus mechanical losses called as the rotational losses or stray losses. Then we are going to get finally the rotational losses plus copper loss is equal to total loss or simply constant losses plus variable losses. So finally I will give here iron loss plus copper loss plus mechanical losses, because iron loss plus mechanical losses is called as the rotational losses. So we are going to get finally rotational losses plus copper losses. So therefore simply we can say that the total loss is the combination of the iron loss plus copper loss plus mechanical loss. Mechanical loss is also called as the iron loss is also called as the core loss, whereas copper loss is also called as ohmic loss, and mechanical loss is also called as the friction and windage losses. So listen carefully. Total loss is a combination of the iron loss plus copper loss plus mechanical loss. Iron loss is also called as core loss. Copper loss is also called as ohmic loss, and mechanical loss is also called as the friction and windage loss. So, but the combination of the iron loss and mechanical loss is called as a rotational losses, or simply we can also call as the stray losses. So therefore, there are rotational losses plus copper loss is nothing but total losses, or simply constant losses plus variable losses. In a shunt and compound DC motor, speed is nearly constant from no load to full load. I have already told you in a shunt and compound DC motors, because compound DC motors characteristics are always going to lie in between the shunt and the series. So in a shunt and compound DC motor, speed is nearly constant from no load to full load. From no load to full load, the speed is almost constant for both shunt and also for the compound. In DC machine, I have already told you torque is equal to, torque is directly proportional to flux into armature current. So if you remember proportionality constant, we are going to get T is equal to K into phi into Ia. Similarly, EB is equal to K into phi into omega. This K is same for both the things. This K is same for both these equations. So you only remember this till you die. So therefore, till you die in this electrical engineering, we have to remember these two important formulas. T is equal to K into phi into A. EB is equal to K into phi into omega. Both these things are always same. Both these things are always same. Rating of generator or motor is its capacity. It tells you about its output. The rating of generator or motor is its capacity. It will tell about its output. So whatever the rating of a given machine, whether it is a generator or motor, it is going to tell its capacity, means it is going to tell you basically about its output. So rating of machine, whether it is generator or motor, basically it's the capacity of its output, how much it can deliver. So therefore, rating of generator or motor is its capacity. It tells you about its output. It is going to basically tell you about its output. So whatever the rating that you see for a given machine, whether it is a generator or motor, basically it is the output. It's the capacity of the output. So the rating of generator or motor is its capacity. It tells you about its output. See, output of machine is equal to shaft power. I already told you, output of machine is equal to shaft power. Basically, it is called as the output of machine is also called as the shaft power. So now we will discuss about the Hopkinson's test. So Hopkinson's test is done on two identical shunt or compound machines which are connected back to back. So it is also called as the back-to-back test. I have already discussed the Hopkinson's test in the DC machines. There we are going to use the two identical machines. One is going to act like a generator and the other is going to act like a motor. So whatever the input taken, it is in the terms of the losses. So whatever the input is equal to the losses which are consumed by both the machines. So by this we are going to find the efficiency of generator. We are going to find the efficiency of both generator and the motor we can find with the help of this Hopkinson's test. So Hopkinson's test is basically done on two identical shunt or compound machines which are connected back to back. So it is also called as the back-to-back test. Fields test is only for the series machine. So we need two identical series machines. Basically, this field test is only for these series machine only. So one is going to act like a generator and the other is going to act like a motor. So therefore, we can find the efficiency of the generator and the motor with the help of this field test. So field test is only for the series machines. So we need two identical series machines. So with the help of this we can figure out the efficiency of the motor and also the generator. So field test is conducted only for the series machines. So we need two identical series machines. One is going to act like a series generator and the other is going to act like a series motor. So with the help of this test we can figure out the efficiency of the series generator and also efficiency of the series motor. Retardation test is connected to figure out the rotational losses. I have already told you retardation test is basically conducted to figure out the rotational losses and the rate of change of kinetic energy is called as the rotational losses. So basically with the help of retardation test we are going to find out the rotational losses and the rate of change of kinetic energy is called as the rotational energy, which is d by dt of kinetic energy is called as the rotational losses. So we can figure out the rotational losses with the help of retardation test and the definition of rotational losses is the rate of change of kinetic energy. So retardation test is conducted to figure out the rotational losses and the rate of change of kinetic energy is called as the rotational losses. So retardation test is basically conducted to figure out the rotational losses and the rate of change of kinetic energy is called as rotational losses. Every machine has intervals that are used for only commutation purpose but not for improving the starting torque. I already told you here the interpulse is going to only improve the commutation but it doesn't have any effect on the improving the starting torque. It will never improve the starting torque. It is only there, it was only there to improve the commutation process or simply it can utilize the cross magnetization under that poles. So under the interpoles whatever the cross magnetization is there it can utilize them or it can also improve the commutation. These are the only two things which can done by the interpoles but not for improving the starting torque. It doesn't have any effect on the improving the starting torque. So every DC machine has interpoles that are used for only commutation purpose but not for improving starting torque. As I already told you, they are basically used for neutralizing the armature reaction, the cross magnetization effect under that interpoles and also to improve the commutation process but they have no effect on improving the starting torque. Two identical lossless series motors connected in series across the DC supply voltage. So two identical lossless series motors connected in series across the DC supply voltage run at a speed of N1 and N2. The ratio of output powers are here always their output power is also equal to 1:1 because output power is equal to EB into IA. So EB is nothing but for each of them it is V by 2 because they are identical. So V by 2 into IA is same for both. So therefore we are going to get 1:1. So therefore two identical lossless series motors connected in series across a DC supply voltage run at a speed of N1 N2. The ratio of their output powers are output power is equal to EB into IA. So EB is equal to for each machine which is nearly equal to V by 2. So V by 2 into IA is to V by 2 into IA. So both are same, they are going to get cancelled. So we are going to get 1:1. So two identical lossless series motors connected in series across the DC supply voltage run at a speed of N1 and N2. Then the ratio of their output powers are 1:1. Two identical having lossless series motors connected in series across the DC supply voltage run at a speed of N1 and N2. The ratio of their output powers are which is N1:N2 because here now it is not a lossless having losses, now it is going to have losses. Then the output power ratio are N1:N2. So two identical having lossless, it is a losses. Now having losses, in the previous case it is lossless, but now it is having losses. Series motors connected in series across the DC supply voltage run at a speed of N1 into the ratio of their output powers are N1:N2 because output power is equal to EB into IA. EB into IA is nothing but now simply we can say that now as the losses are there, so we don't know as the losses are there, EB is never equal to V by 2, EB is proportional to N1 and EB2 is proportional to N2. So EB1 is proportional to N1 and EB2 is proportional to N2. IA is same for both the machines. So simply we can say N1:N2 because EB1 is proportional to N1, EB2 is proportional to N2. IA is same for both the things. So therefore simply we are going to get N1:N2. If it is lossless means we can say EB is nearly equal to V by 2. Lossless means EB is nearly equal to V by 2. If losses are there means EB is never equal to V by 2 because we can't tell that. Now it is proportional to N1 and N2. Like that we have to apply here. So loss less means N1 is to N2. Loss are there means N1 is to N2. See, loss less means 1 is to 1. Loss are there means N1 is to N2. So in DC series motor, I have already told you, in a DC series motor, the flux is directly proportional to armature current. So torque is directly proportional to flux into armature current. Flux is directly proportional to Ia. So Ia to Ia is again Ia square. So T is proportional to Ia square. And the power is proportional to T into omega. So T into speed. And I can replace T by Ia square. So we are going to get power is proportional to speed into Ia square. And I have already told you EB is proportional to M into phi. As the phi is proportional to Ia, then we are going to get like this, which is EB is proportional to N into Ia. So EB is proportional to N into Ia. The no load speed of a separately excited DC motor is N0. The no load speed of a separately excited DC motor is N0. And the armature resistance drop and the pressure drop are neglected. And the field current is kept constant at rated value. And then the speed of the motor is constant at any load condition. I have already told you the no load speed of a separately excited DC motor is N0. And the armature resistance drop and the base drop are neglected, and field current is kept constant at a rated value, and then the speed of the motor is constant for any load condition, because here we can see clearly, as we are going to neglect the armature resistance drop and the base drop, so EB is always equal to V. It is a DC motor, so the supply is a DC motor, so EB is nearly equal to supply voltage, and the field is also constant, field current is a constant, so flux is also constant. So now we can say that as EB is nearly equal to V and IB is always constant. So what is the EB is directly proportional to M into phi. So M is equal to directly proportional to EB by phi. As EB is equal to V and flux is equal to always constant, the ratio of V by flux is always constant. So EB by phi is always constant for any load condition. So speed is always constant for any load condition, because V by phi is always constant. So at any load, if you keep any load at this condition, definitely speed is always constant, is equal to no load speed itself. So induction generators are rarely used. Induction generators are rarely used. But in induction motors, 3-phase are used in industrial applications, whereas single phase are used in small industrial, commercial and domestic applications. And these induction motors are most popular. I have already told you, out of synchronous generator and induction generator, we mostly prefer the synchronous generator but not the induction generator. So simply we can say that induction generators are rarely used. But in induction motors, 3-phase are used in industrial applications, whereas the single phase are used in small industrial, commercial, domestic applications. And these induction motors are mostly popular. I have already told you the induction motors are most popular when compared to synchronous motors. So therefore, these are mostly used in all the industrial applications. Synchronous generators are more popular and the induction motors are very popular. So therefore, induction generators are rarely used, but in induction motors, 3-phase are used in industrial applications, whereas the single phase are used in small industrial, commercial, domestic applications. And these induction motors are most popular. For to obtain rotating magnetic field, 3-phase supply with 120-degree time displacement and 3-phase winding of 120-degree space displacement compulsory. I already told you, if these two conditions are satisfied, then only we are going to get a rotating magnetic field. See here, in a 3-phase supply, there should be 120-degree time displacement, and the 3-phase winding with respect to space, they should have 120-degree space displacement. If these two conditions are satisfied, then only we are going to get the rotating magnetic field. So for to obtain the rotating magnetic field, 3-phase supply with 120-degree time displacement and 3-phase winding of 120-degree space displacement is compulsory, then only we are going to get the rotating magnetic field. If any of these two conditions are not, if any one of these two conditions is not satisfied, then you are not going to get a RMF. These two conditions should be satisfied, then only we are going to get a rotating magnetic field. So therefore, for to obtain rotating magnetic field, 3-phase supply with 120-degree time displacement and 3-phase winding of 120-degree space displacement is compulsory to get the rotating magnetic field. So if you want to obtain the rotating magnetic field, 3-phase supply with 120-degree time displacement and 3-phase winding of 120-degree space displacement is compulsory to get the rotating magnetic field. Induction motors are operate on AC supply, so no need of commutator and no armature reaction. I already told you induction motors are going to operate on the AC supply, so there is no need of commutation and there is no armature reaction. So armature reaction is not present, and also commutator is also not present in the induction motors, because always we are going to operate on the AC supply. As induction motors are going to operate on the AC supply, so no need of commutator and no need of the no armature reaction is present in the induction motors. As induction motors are operated on AC supply, so no need of commutator and also no need of armature reaction. Three-phase induction motors are self-starting, whereas the single-phase induction motors are not self-starting. I've already told you, three-phase induction motors are always self-starting, whereas single-phase induction motors are non-self-starting. These are very cheap in construction, least maintenance, operate at good efficiency, but it won't give excellent speed control like DC shunt motors and no high starting torque. So we can say that these three-phase induction motors are self-starting, whereas the single-phase induction motors are not self-starting. And these induction motors are very cheap in construction and the least maintenance is required, and they are going to operate at the good efficiency, but it won't give excellent speed control like DC motors or DC shunt motors and no high starting torque. So only these are the two disadvantages of the induction motors, because they can't give excellent speed control techniques and also no high starting torque. These are the only two disadvantages of the induction motors, but even though they are preferred. So therefore we can say that they can't give excellent speed control characteristics like DC shunt motors and no high starting torque. Only these are the two important disadvantages of the induction motors. Three-phase induction motors are the self-starting, whereas the single-phase induction motors are not self-starting. These induction motors are very cheap in construction, least maintenance, and they are going to operate at a very good efficiency, but it won't give excellent speed control characteristic like DC shunt motor and no high starting torque. They can't give, they don't have excellent speed control characteristic like DC motors, and also they have no high starting torque like DC motors. So only these are the two important disadvantages of the induction motors when compared to DC motors. So three-phase induction motors are self-starting, whereas the single-phase induction motors are not self-starting. So even though these induction motors are very cheap in construction, least maintenance, they are going to operate at a very good efficiency, but it won't give excellent speed control like the DC motors, and they have no high starting torque like DC motors. Induction motors can handle twice the rated load and nothing happens. See, induction motors can even handle twice the rated load. Whatever the rated load capacity, they can handle twice that, but even though nothing is going to happen, means nothing damage is going to happen, but still they can handle twice the rated load. So this is one of the important advantage of the induction motors. That is the reason these are mostly preferred. So induction motors can handle twice the rated load and nothing is going to happen to the induction motors. So induction motors can handle twice the rated load and still nothing is going to happen to it. So induction motors can handle twice the rated load and nothing is going to happen to it. So induction motors can handle twice the rated load and still nothing is going to happen to them. If you give DC supply to poles, their polarity is fixed, but if you give AC supply, the polarity of the poles is changing continuously. I have already told you, if you give DC supply to your poles, their polarity is always fixed. But if you give AC supply, as the flux is changing for positive cycle in the positive direction, the negative cycle is in negative direction, so therefore the poles are going to change continuously. So if you give a DC supply to the field winding, the poles are going to always fix their polarity, but if you give AC supply to a field winding, the poles are going to change the polarity continuously. As I have already told you, the direction of rotation of magnetic field is in the direction of the phase sequence. So whatever the direction of the phase sequence is the direction of the rotating magnetic field. The direction of rotation of the magnetic field is in the direction of the phase sequence. So whatever the phase sequence, then we can simply say that is the direction of the rotating magnetic field. See, phase sequence means what? See, which signal is having the initially zero is coming earlier. The first zero which is coming is the first, second zero is coming second, third zero is coming the third. So out of three signals, the first is zero, the positive going zero, which is coming earlier, it is the first phase sequence, then go for the second and then go for the third. So the direction of the phase sequence is the direction of the rotating magnetic field. There should be at least a air gap between the stator and rotor in induction machine. So less is the air gap means less is the magnetizing current required to keep the constant flux. So you see, always you have to keep a less air gap between the stator and the rotor in the induction machine, because we need less amount of magnetizing current to produce the constant flux. So therefore, simply we can say that there should be less air gap between the stator and rotor in the induction machine if you want to keep the flux as a constant. Less is the air gap, the less is the magnetizing current required. More is the air gap, more is the magnetizing current to keep a constant rated flux. So always try to operate at least air gap between the stator and the rotor in an induction machine. There should be least air gap between the stator and rotor in the induction machine. The outer frame of induction machine is made of cast iron for small machines, steel and aluminium for large machines, and this won't carry any flux, and these are laminated to reduce the eddy currents and hysteresis. The outer frame of induction machine is made of cast iron for small machines, steel and aluminium for large machines, and this won't carry any flux, and these are laminated to reduce the eddy current and hysteresis losses. I already told you, in a DC machine, yoke is non-laminated, but it is useful for flux completion. Poles are laminated, and the armature core is also laminated. And the armature core is basically made of silicon steel. I have already told you. So we are going to do the lamination to reduce the eddy current losses. Whereas in the case of the induction machine, the outer frame of the induction machine is made by cast iron for small machines, and for steel and aluminium for the large machines we are going to use here. And this won't carry any flux. There is no this outer frame of induction machine will never carry any flux, but these are laminated to reduce the eddy current and hysteresis losses. This outer frame is basically laminated because to reduce the eddy current and also the hysteresis. So this is a very important point. So always the outer frame of induction machine is made of cast iron for the small machines, steel and aluminium for the large machines, and this won't carry any flux, and these are laminated to reduce the eddy current and also the hysteresis. So this is a very important point that you always have to remember. The outer frame of induction machine is made of cast iron for small machines and the steel and aluminium for large machines, and this won't carry any flux, and these are laminated to reduce the eddy current and also the hysteresis. Three types of slots present on the stator to hold the windings of supply are closed slot, open type slot, and the semi-open type slot. I have told each and everything in the induction machine. I have did the comparison of each and everything also I have already told. So basically there are three types of slots present on the stator to hold the windings of supply are the closed slot, open type slot, and the semi-open type slot. So these are the three types of slots which are present on the stator to hold the supply windings. So therefore, three types of slots present on the stator to hold the windings of supply are the closed slot, open type slot, and the semi-open type slot. So these are the three types of slots which are going to present on the stator to hold the supply winding wires. So therefore, the three types of slots present on the stator to hold the windings of supply are the closed slot, open type slot, and the semi-open type slot. Open type slot are easy to design and used for large rating machines. Closed slot type and semi-open type slot are complicated to design. See, open type slot are easy to design and used for large rating machines, whereas the closed slot type and the semi-open type slot are very complicated to design. See, open is very easy to design and basically they are used for the large rating machines, whereas the remaining two, the closed slot type and the semi-open type slot, are very complicated to design. I already told the comparison of each and everything in the induction machine. Please go back to the induction machine concept, then you will know each and everything regarding the comparison of all these slots. So basically there are three types of slots. Out of that, open type slots are easy to design and these are basically used for the large rating machines, whereas the remaining two, the closed slot type and the semi-open types, are very hard to design. All machines draw reactive component to produce flux. I already told you, all the machines are going to draw the reactive component of power to produce the flux. The reactive component, the reactive power is going to produce the flux. So all machines are going to draw the reactive component of power to produce the flux. So all machines are going to draw the reactive power basically to produce the flux in that machine. So all the machines are going to draw the reactive power component to produce the flux. Rotating magnetic field must go through air, so high reluctance in air. So magnetic drawn current is high. Slots are responsible for distortion in flux in space, non-sinusoidal. Space harmonics are more in open type slot, low in closed type slot, and moderate in the semi-open type slot. I have already told you, this is a very important point that I have already told you, which is the rotating magnetic field must go through air. So high reluctance in air. So magnetic current drawn is very high. Slots are responsible. So therefore we can say that simply the rotating magnetic field must go through air. So high reluctance in air. So magnetic current drawn must be high. See, air, basically air has the less permeability. So therefore the reluctance is very higher. As reluctance of air is very higher, you need more amount of magnetic current to produce the rated flux. So rotating magnetic field must go through air. So high reluctance in air. So therefore, magnetic current drawn is very high to produce the rated flux. Slots are responsible for distortion in flux in space. See, basically the slots on the stator and the slots in the rotor. These slots are going to responsible for the distortion of the flux in space. If there are no slots, then definitely whatever the flux in the air gap is pure sinusoidal. But because of the slots on the stator and the rotor, there is a distortion in the flux. So flux is not at all pure sinusoidal, it will be non-sinusoidal. So because of this, harmonic components are going to get present. So space harmonics are more in open type slot and low in closed type slot, and moderating the semi-open type slot. So whatever the space harmonics are basically very high in the open type slot and moderate in the semi-open type and very less in the closed type slot. These space harmonics are very high in the open type slots and the moderate in the semi-open type and very less in the closed type slots. So see, because of these slots only, the slots which are present on the stator and the rotor, they are going to distort the flux in the space. So now the flux will be not at all pure sinusoidal, it will be non-sinusoidal. So because of this non-sinusoidal, harmonics are going to get produced in the flux. So these space harmonics are basically very high in the open type slot and moderate in the semi-open type and very less in the closed type of slots. Preferable slots in induction machine in the stator and the rotor is semi-open type always. See, always out of these three slots, we are going to always prefer only the semi-open type slots. So semi-open type slots are very preferred on the stator and also on the rotor of an induction machine. So the preferable slots in induction machine in the stator and the rotors is semi-open type always, because all the things are moderate here. Then we go for this one. If you compare open type and closed type, in the semi-open type all the things are moderate. Nothing is very low, nothing is very high. Everything is in moderate region. So we prefer this one only. So therefore, the preferable slots in induction machine in the stator and the rotor is always semi-open type always. Semi-open type slots are always preferred for the stator and the rotor slots in an induction machine. The preferable slots in the induction machine in the stator and the rotor is always semi-open type always. In large ratings, we use open type slot always. In large ratings, we use open type slots always. So in the large ratings, I already told you, if you want the high rating machines, if you want to go for the high rating machines, then we always go for the open type slot, because open type slots are very easy to design and basically these are used for the large rating machines. Whereas the closed slot type and the open slot type are very complicated to design. I already told you, open type slots are very easy to design and basically these are used for the large rating machines. Whereas the closed slot type and the semi-open type slot are complicated to design. So in large ratings, we use the open type slot always, in induction and also in the synchronous machine. So in large ratings, we use open type slot always in the induction and also in the synchronous machine. So I already told you, in large ratings, we go for the open type slots in both the stator and the rotor in the induction and also in the synchronous machines. Closed slot in squirrel cage rotors is in small ratings is only we use. So closed slot in squirrel cage rotors in small ratings only we use. For large rating squirrel cage rotors, we use any closed slot type. So if you compare in the squirrel cage motors, in the squirrel cage rotors for small ratings we use the closed slot, and for higher ratings we go for the semi-closed type. So in the squirrel cage rotors, for small ratings we go for the closed slot, and for the higher ratings we go for the semi-closed type. So closed slot in the squirrel cage rotors in small ratings only we use, and for large ratings squirrel cage rotors we use the semi-closed type. So in the squirrel cage rotors, for smaller ratings we go for the closed slot types, and for large ratings we go for the semi-closed type slots. DC motor armature core uses open type slot because of less reactance, so less ER, so less sparks. I already told you, DC motor armature core uses open type slot because of less reactance, so less ER, so less sparks. Whenever the reactance is less, the reactance voltage is also very less, so sparks are also very less. That is the reason in the DC motor we go for the open type slots, because in the open type slots the inductance is very less or the reactance is very less, so therefore the reactance voltage is also less, because the reactance voltage is directly proportional to inductance, reactive inductance. So therefore less is the reactance, less is the inductance, less is the ER, so less sparks. So therefore in the DC motor, the armature core, basically in the DC motor the armature core is made up of the silicon steel. The armature core is always in the laminated type. I already told you, It is going to use the open type slot because of less reactance. So ER is less, so sparks are also very less. As air gap between the stator and the rotor decreases, then leakage flux decreases, and so less IM is needed. I already told you, if the air gap between the stator and the rotor is very less, then definitely the IM, the magnetizing current required to get the rated flux is very less. So more is the air gap, more is the magnetizing current, less is the air gap, less is the magnetizing current required to get a rated flux. As the air gap between the stator and the rotor decreases, the leakage flux decreases, and so less magnetizing current is needed. If the air gap is very lesser, the magnetizing current required is lesser. If the air gap is more, the amount of requirement of magnetizing current is very high. Frames are used only for mechanical protection. I already told you, in a DC machine, the frames are only used for mechanical protection. There is no flux completion path there, and also they are basically laminated. The frames are always being laminated, and I already told you, for smaller machines we go for the outer frame is made by cast iron, and for higher machines we go for the steel and the aluminium. I already told you, the outer frame of induction machine is basically made of cast iron for the small machines and the steel and aluminium for larger machines, and this won't carry any flux, and these are laminated to reduce the current and hysteresis losses. So simply we can say that the frames, although the frames used for the induction machine are basically used for only mechanical protection. Stator of synchronous is always connected in star, and the stator of induction is connected in star or delta. I have already told you, the stator of synchronous is always connected in star, and the stator of induction is always connected in star or delta based on the applications. So we can see the stator of the synchronous machine is always connected in star fashion, whereas the stator of induction, it can be connected in either star or delta. So this is a very important point. Always in a synchronous machine, the stator winding is always connected in a star fashion, whereas in the case of induction, the stator can be connected either in the star or either in the delta. So based on the applications, we are going to change it. So always the stator of a synchronous machine is always connected in the star fashion, whereas the stator of the induction machine can be either connected in the star or either it can be connected in delta. So this is a very important point. The stator of the synchronous machine is always connected in a star fashion, whereas the stator of the induction machine is connected in either star or delta. The slots in the stator are always divided by 3 or 6. It's a very important point. Whatever the slots in the stator are always divisible by 3 or 6. So we are going to choose only those slots which are divisible by either 3 or divisible by 6 in any machine. So whatever the slots in the stator are always divisible by either 3 or either by 6. So whatever the slots in the stator are always divisible by either 3 or 6. The slots in the stator, whether it is a induction machine or a synchronous machine, we are going to choose those number of slots which are always divisible by either 3 or either divisible by 6. So therefore, the slots in the stator, whether it is a synchronous machine or induction machine, we are going to choose the number of slots which are always divisible by either 3 or 6. Beta is called as the slot angle. Slot angle means the angle between the two adjacent slots, and the space displacement contributed by each slot in electrical degree. Due to space displacement of coils, we get time displacement of voltage in coils. This beta is nothing but 1 degree by slots per pole. I have already told you beta is nothing but slot angle. It is the ratio of the 1 degree by pole pitch. Pole pitch means slots per pole. See, pole pitch basically the distance between the two adjacent poles, the center to center distance between the two adjacent poles. It is actually measured in terms of number of slots per pole. It is going to measure the terms of number of slots per pole or number of conductors per pole. It can measure in either number of slots per pole or the number of conductors per pole. Like that we can discuss. So therefore, we can say that due to space displacement, we are going to get the time displacement in the voltage used in the coils also. I have already told this in the induction machine itself. So whatever this beta is called as the electrical angle between the two adjacent slots. So beta is called as the slot angle, or we can say simply the angle between the two adjacent slots. So beta is also called as slot angle. The space displacement contributed by each slot in the electrical degree. Due to space displacement of coils, we get time displacement of voltage in the coils. I have already told you, due to space displacement of coils, we are going to get a time displacement of voltage in the coils. So therefore, beta is called the slot angle. The space displacement contributed by each slot in electrical degree. It is a space displacement contributed by each slot in electrical degree. Due to space displacement of coils, we are going to get the time displacement of voltage in the coils. I have already told you, due to space displacement of coils, we are going to get a time displacement of voltage in the coils. So beta is equal to 180 degree by pole pitch. Pole pitch is number of slots per pole. Pole pitch means the center to center distance between the coils and poles. It is basically defined in the terms of number of slots per pole or number of connectors per pole. All these things I already told you. So beta is called the slot angle. It is a space displacement contributed by the each slot in electrical degree. Due to space displacement of coils, we are going to get the time displacement of voltage in the coils. So beta is equal to 180 degree by pole pitch. Pole pitch is slots per pole. Phase group or phase belt is defined as number of some conductors or slots belonging to same phase is equal to n. So phase group or phase belt is defined as the number of adjacent conductors or slots belonging to the same phase. It is represented by symbol m. So phase group or phase belt is defined as the number of adjacent conductors or slots belonging to the same phase is equal to m. So phase group or phase belt. So phase group or phase belt is defined as the number of adjacent conductors or slots belonging to the same phase. It is represented by symbol of m. So phase group or phase belt is defined as number of adjacent conductors or slots belonging to same phase. See, suppose in a two slots, the two slots having the windings of same phase are, then we can say m is equal to 2. Suppose if the three slots adjacent to each other and these three slots have the same winding of phase r, then we can say m is equal to 3. So phase group or phase belt is defined as the number of adjacent conductors or slots belonging to the same phase. So phase group or phase belt is defined as the number of adjacent conductors or slots belonging to the same phase is equal to m. So phase spread is defined as the total angle contributed by the phase group is called as the phase spread, which is m into beta. So basically we can say that generally three phase winding have 100 degree or 60 degree phase spread. 60 degree is called as the narrow phase spread and 100 degree is called as the wide phase spread. I have already told this important point. So phase spread is defined as the total angle contributed by the phase group is called as the phase spread, which is equal to m into beta. Generally three phase winding will have 100 degree or 60 degree phase spread. 60 degree is called as the narrow phase spread and 100 degree is called as the wide phase spread. So phase spread is defined as the total angle contributed by the phase group is called as the phase spread is equal to m into beta. So generally three phase winding have 100 degree or 60 degree phase spread. So I have already told you phase spread is defined as the total angle contributed by phase group is called as the phase spread, which is equal to m into beta. The phase spread is defined as the total angle contributed by the phase group is called as the phase spread, which is equal to m into beta. So generally three phase winding has 100 degree or 60 degree phase spread. 60 degree is called as the narrow phase spread and 100 degree is called as the wide phase spread. But narrow phase spread 60 degree will offer better voltage and power ratings, therefore commonly preferred in three phase winding designs. I have already told you with the help of narrow phase spread, whatever the power and whatever the power ratings and the voltage you are going to get is higher when compared to 120 degree. So always we are going to use the 60 degree only. So but narrow phase spread 60 degree will offer better voltage and power ratings when compared to 120 degree. So therefore commonly preferred is three phase winding design. So therefore 60 degree narrow phase spread is always used in our three phase winding designs. So phase spread is defined as the total angle contributed by phase group is called as the phase spread is equal to m into beta. Generally three phase windings have 100 degree or 60 degree phase spread. 60 degree is called as the narrow phase spread, whereas the 100 degree is called as the wide phase spread. But narrow phase spread 60 degree will offer better voltage and power ratings, therefore commonly preferred in three phase winding designs. DC machine windings are closed, whereas the AC machine windings are open. I have already told you DC machine windings are always closed. In a DC machine, whatever the armature winding that you are going to use, it is always closed in nature. Whereas in the AC machine, whatever the windings are always open, because the stator, see we can see the stator, in the stator we are going to keep the armature winding. It is basically open in nature to give a supply, so therefore the DC machine windings are always closed in nature, whereas the AC machine windings are always open in nature. So DC machine windings, whatever the DC machine windings you see, whether the field winding or whether the armature winding, both are always closed. Whereas in the AC machine, whatever the armature coil present on the stator are basically open in nature. So therefore simply we can say that DC machine windings are always closed, whereas the AC machine windings are always open. See, I have already told you M is nothing but I have already told you here basically what is the meaning of M means the phase group or phase belt is defined as the number of adjacent conductors and slots belonging to same phase. It is called as the M. M means phase group or phase belt, which is defined as the number of adjacent conductors and slots belonging to the same phase is equal to M. So M is equal to slots per poles per phase. Basically it is going to tell you the number of slots the adjacent slots which are having the same phase windings. So slots per pole per phase. Suppose if you are going to get M as integer, then integral slot winding and full pitch windings is preferred. Whenever M is equal to integer, always integral slot winding and the full pitch winding is always preferred. If suppose M is equal to non-integer, then fractional slot winding and short pitch type winding is preferred, and it always helps to reduce the some order of harmonics. I already told you, whenever M is equal to integer, integral slot winding and the full pitch winding is preferred, whereas M is equal to non-integer means the fractional slot winding and the short pitch type winding is preferred, and it always helps to reduce some order of harmonics, because short pitch winding is always going to remove some of the harmonics. I have already told this important point. So whenever M is equal to integer, we are going to use the integral slot winding and we are going to use full pitch winding is preferred, whereas M is equal to non-integer, it is called as a fractional slot winding and we are going to use the short pitch type of winding. So whenever the coil span is lesser than pole pitch, it is called as a short pitch type of winding, and it is preferred, and it is always helps to reduce the some order of harmonics. You see, if number of coils is equal to number of slots, then this belongs to double layer winding in stator. I already told you double layer winding. Let me assume there are 30 coils. If 30 coils means each coil has each coil has 2 coil sets. So 30 coils means 60 coil sets. In double layer winding, we have to keep 2 coil sets in one slot. So therefore, 60 coil sets, 2 coil sets in one slot means 60 coil sets we have to keep in 30 slots. So simply we can say the number of slots is equal to number of coils in case of double layer winding. So therefore, if number of coils is equal to number of slots, then this is going to belongs to double layer winding in stator. So this I have already told you. So therefore, for large voltages, star connection is preferred in stator because phase voltage is always low. So if you want a high line voltage, then definitely phase voltage is always less in a star connection, because line is equal to √3 into phase voltage. So line voltage is equal to √3 into phase voltage. So phase voltage is equal to line voltage by √3. So for large voltages, star connection is preferred in stator because phase voltages are always low. So therefore, for large voltages, star connection is preferred in stator because phase voltages are always less. So for large voltages, star connection is preferred in stator because phase voltages are always low. So for large voltages, star connection is preferred in stator because phase voltages are always low. So for large voltages, star connection is preferred in stator because phase voltages are always low. The rotor in induction machine are of two types. They are squirrel cage and a slip ring or wound rotor. I have already told you the rotor in induction machine are of two types. One is called as the squirrel cage rotor and the other is called as the slip ring or wound rotor. So you can call anything slip ring rotor or wound rotor, because slip ring is basically we can connect the external resistance from outside to that winding to the rotor winding, so we can increase the starting torque. The rotor in induction machine are of two types. One is called the squirrel cage rotor and the other is called as the slip ring rotor or the wound rotor. So rotor has thick laminations, so no core loss in the rotor but present only in the stator. So whatever the rotor, we are going to use a very thick laminations. So no core loss in the rotor but will present only in the stator, because see, I have already told you we are going to neglect the core loss in rotor because we are going to use the thick laminations. So whenever we are going to use the thick laminations, definitely we can say the core losses are very less in the rotor. That is the reason we are going to neglect the core losses, but only we are going to consider the copper losses in the rotor. So therefore, whatever the core losses we are going to neglect, only thing that we are going to consider is only the copper losses. So core losses have been neglected in the rotor because they have the thick laminations. Because rotor has a thick laminations, so no core losses in the rotor but present only in the stator. See, whatever the rotor that we are going to choose here, it is having the thick laminations. So there will be no rotor, there will be no copper loss, there will be no core loss in the rotor. Only copper loss are going to present in the rotor. In small machines, die-cast aluminium bars used in rotor, but in large machines, copper bars are used. See, in the small machines, the die-cast aluminium bars are used in the rotor, but in large machines we use the copper bars are used. So small machines means we have to use the aluminium bars, but for large machines means we have to use the copper bars, because copper has less resistance when compared to aluminium. So small machines means the rotor bars are made by aluminium, and large machines means we have to use the copper bar because copper has a less resistance compared to aluminium. So in a small machines, so die-cast aluminium bars are used in the rotor, whereas in the large machines copper bars are used. So small machines means basically we have to use the die-cast aluminium bars, and large machines means we have to use the copper bars. Copper has less resistance when compared to aluminium. Bars are slightly inclined or screw slots to reduce the cogging effect. So means simply locking effect. Cogging effect means the locking effect. The locking effect between the stator and the rotor can be removed if you just give a screwing. Screwing just slightly incline the rotor, incline the bars, rotor bars by a small amount of angle. So therefore we can reduce the cogging effect, or simply we can say locking tendency between the stator slots and the rotor slots. We can reduce just by slightly incline the rotor slots. So therefore we can say with the help of screwing we can prevent the crawling and clogging, but the efficiency is also going to get decreased because of that, because the length of copper bar increases because of the screwing. So length is more means the resistance is more, so copper loss, the losses are the whatever the copper loss in the rotor will increase, so efficiency will decrease. So listen carefully. With the help of screwing of rotor slots, we are going to neglect the reduce the cogging and the crawling effects, but the efficiency will be decreased, because as you are screwing the rotor slots, the length of the bars are going to get increased. As the length increases, the resistance increases, so the copper loss increases, so therefore the rotor copper loss increases, so efficiency will decrease. I have already told this important point. So bars are slightly inclined screw slots to reduce the cogging effect. The slots on rotor and the slots on stator are always equal. I have already told you, no matter whatever the case, see, in the case of induction motor, see, listen, in the case of squirrel cage induction rotor, in this case of squirrel cage rotor, always by nature itself, whatever the poles assigned on the stator, definitely same poles are also going to assign itself on the rotor for a squirrel cage rotor by nature itself. See, suppose in a squirrel cage rotor, if the stator has 4 poles, by nature itself, the poles, 4 poles are going to get induced on the rotor also. So listen carefully. Suppose for a squirrel cage rotor, if the stator has 6 poles, definitely by nature itself, 6 poles are also going to get inclined on the stator on the rotor also. So this is a very important point. Whatever the slots on the rotor and the slots on the stator are always equal. So whatever the slots, the number of slots used on the stator should be always equal to the number of slots on the stator, and the rotor should be always equal. The number of slots on the rotor and the number of slots on the stator are always equal. The number of slots on the rotor and the number of slots on the stator are always equal in number. Induction rotors are very simple to design than any other rotors. Induction rotors are very simple to design than any other machine rotors. Induction machine rotors are easily designed when compared to any other machine rotor. So induction rotors are very simple to design when compared to any other machine rotors. So induction rotors are very simple to design than any other machine rotors. In this, starting torque is low, but running torque is excellent. And what I told you, the starting in the squirrel cage rotor, simply we can say in this, the starting torque is low, but the running torque is very excellent. So therefore simply we can say, during starting, high resistance bars increases torque, but during running, high resistance bars decreases the torque. I have already told this point. Basically we can say that simply in the starting torque is low, but running torque is excellent. So during starting, high resistance bars increase the torque, but during running, high resistance bar decreases the torque. And what I told you, in an induction machine, the more is the resistance, the starting torque is very higher. But if more is the resistance during the running condition, the torque will decrease. So this is a very important point. So we can say that during the stable region or during the starting conditions, always the starting torque is directly proportional to rotor resistance. But during the running conditions, if more is the rotor resistance, then definitely the torque will reduce. That is the reason we have to only introduce the rotor resistance only during the starting condition, but not during the running conditions. So we have to include the starting resistance. We have to include the starting resistance only during the starting condition, but not during the running condition, because the resistance, more is the resistance during the starting torque will be very high. More is the resistance, the rotor resistance during running, less is the torque. Slip ring induction motor windings are present. I already told you, in a slip ring induction motor, windings are present on rotor also. So we keep same number of coils on rotor as it is on the stator, and the terminals we take it outside. In this stator, 3-phase winding can be either carried in star or delta, but in rotor, 3-phase winding only star connection is preferred. I have already told you, in a slip ring induction motor, windings are present on the rotor also. So windings are present both on the stator and also on the rotor in case of slip ring induction motor. We keep same number of coils on rotor as it is on the stator. The number of coils on the stator and the number of coils on the rotor should be always equal. And also we keep same number of coils on rotor as it is on the stator, and the terminals we take it outside. And the terminals we are going to take it outside. In this stator, three-phase winding can be either connected in star or either delta, but in rotor, three-phase winding only star connection is preferred. I already told you very important point. In a synchronous machine, the armature coil present on the stator is always connected in a star connection, whereas in an induction machine, the stator, the coil in the stator can be connected either in a star or either in a delta, but the rotor winding should be connected always in star connection only. So listen carefully. In a synchronous machine, whatever the armature coil present on the stator should be always in star connection only. Whereas in the DC machine, the winding on the in the DC machine, whatever the winding on the stator should be connected either in star or either in delta, whereas the winding on the armature should be always connected in star only. So these are the important points that you always have to remember. So therefore, in a slip ring induction motor, the windings are present on the rotor also. We keep same number of coils on the rotor as it is on the stator, and the terminals we take it outside. In this stator, three-phase winding can be either connected in star or delta, but in rotor, three-phase winding only star connection is preferred. Always the number of poles on stator and the number of poles in the rotor must be same, then only torque produces. It's a very important point. See, I have already told you, always the number of poles on the stator and the number of poles in the rotor must be always same, then only the torque is going to get produces. See, the number of poles on the number of poles on stator and the number of poles on the rotor should be always same, then only the torque produces. If they are unequal, the torque will never produce and the rotor will never rotate. So whatever the poles present on the stator should be always equal to number of poles in the rotor, then only the torque is going to get produced. See, whereas in the squirrel cage induction motor, by nature itself, the number of poles on the stator is going to become equal to number of poles. The number of poles on the stator is always going to become equal to number of poles in the rotor by nature itself. Whereas in the slip ring induction motor, we have to make it equal by winding the proper winding on the rotor of the slip ring induction motor. So therefore, we always have to take the number of poles on the stator is equal to number of poles on the rotor. In case of slip ring induction motor, we have to make it. But in the case of squirrel cage induction motor, by nature itself, it is going to become automatically. But in the slip ring induction motor, we have to make it. On squirrel cage rotor also, automatic formation of poles will occur, and which is equal to number of poles in the stator. And already told you, on the squirrel cage rotor also, automatic formation of poles will occur on the rotor, and which is equal to number of poles in the stator. So always, automatically, by nature itself, by God grace itself only, the number of poles in the rotor will be always equal to number of poles in the stator by God's grace only. So therefore, on squirrel cage rotor also, automatic formation of poles will occur on the rotor, which will be always equal to number of poles in the stator. So therefore, simply we can say that on squirrel cage rotor also, automatic formation of poles will occur on the rotor, which is equal to the number of poles in the stator with the help of God's grace. But for the slip ring induction motor, we have to make the number of poles in the rotor is always equal to number of poles on the stator. We can figure out the number of phases automatically present on squirrel cage rotor. We can figure out number of phases automatically present on the squirrel cage rotor. So we can figure out the number of phases automatically present on squirrel cage rotor with the help of this one. The number of phases is equal to, I have already told you, the number of phases on the stator is always equal to number of phases on the rotor is equal to, is the ratio of number of slots in stator by number of poles in stator. So if you do the division of number of slots in stator by number of poles in stator, you are going to get the number of phases. The number of phases on the stator and the number of phases on the rotor is always equal. The number of poles on the stator and the number of poles in the rotor is always equal. And the number of slots in the stator and the number of slots in the rotor is also equal. So listen carefully. The number of slots in the stator and the number of slots in the rotor are always equal. And the number of poles in the stator and the number of poles in the rotor are always equal. And the number of phases on the stator and the number of phases on the rotor are also equal. So these are the very three important points. The number of slots is same in both the stator and also in the rotor. The number of phases is same in both the stator and also in the rotor. The number of poles is same in both stator and also in the rotor. So therefore, we can easily figure out the number of phases automatically present on the squirrel cage rotor, which is number of phases is equal to, it is the ratio of the number of slots in stator by number of poles in stator, because the number of slots in stator is equal to number of slots in rotor, number of poles in stator is equal to number of poles in rotor, and the number of phases in stator is equal to number of phases in rotor. So therefore, the number of phases is equal to ratio of the number of slots in stator by number of poles in stator. For high starting torque, we use slip ring induction motor, but majority of induction machines are squirrel cage induction motors. So I already told you, if you want a very high starting torque, then only use the slip ring induction motor, because in a slip ring induction motor, the rotor has a windings. So with this windings, we can connect the external resistance. So we can use it for the only for starting conditions, and during the running conditions, we can remove that external resistance with the help of black metal joining across the terminals of the armature winding present on the rotor. So this is a very important point. So therefore, if you want high starting torque, then only use the slip ring induction motors, but in majority of the cases we are going to use only the squirrel cage induction motor. So for high starting torque, we use the slip ring induction motor, but majority of the induction machines are squirrel cage induction machines. The flux in air gap cuts both the stator and the rotor, so it produces voltage in both. I already told you the flux in air gap is going to cut both the stator and the rotor coils. So it is going to produce voltage in both, which is E1 is the induced voltage in stator due to RMF, E2 is the induced voltage in rotor due to RMF. These are always per phase values. See, whatever the flux present in the air gap, it is going to cut both the stator coils and also the rotor coils. So it is going to produce some voltages in both the stator and the rotor coils per phase, which is E1 is called as the per phase induced voltage in stator due to RMF. E2 is called as the per phase induced voltage in rotor due to RMF. So this is a very important point that you always have to keep understanding the concept behind this one. So whatever the flux in the air gap is going to cut both the stator coils and also rotor coils. So it is going to produce voltages in both the stator and also the rotor coils. So E1 is called as the per phase induced voltage in stator due to RMF. E2 is called as the per phase induced voltage in rotor due to RMF. So therefore, whatever the flux in the air gap is going to cut both the stator coils and also the rotor coils. So it is going to produce some voltage in both stator coils and also the rotor coils. E1 is called as the per phase induced voltage in stator due to RMF, and E2 is called as the per phase induced voltage in rotor due to RMF. Induction machine is a single excited machine, whereas basically synchronous machine is a double excited machine. I have already told you, induction machine is a single excited machine, whereas the synchronous machine is a double excited machine. It is similar to rotating type transformer. I have already told you, induction machine is a single excited machine and it is similar to a rotating type transformer. So induction machine is basically a singly excited machine and is similar to a rotating type transformer. So induction machine is a singly excited machine and it is similar to a rotating type transformer. I already told you X2 dash is equal to S into X2, which is the reactance of the rotor during the running condition is equal to slip times the reactance during the standstill condition. As the rotor speed increases, its reactance decreases, because as the rotor speed increases, what is going to happen? As the rotor speed increases, the slip decreases. The slip decreases means this overall value will decrease. So therefore, we can say as the rotor speed increases, then definitely this overall reactance will decrease. As this reactance decreases, definitely we can say angle theta decreases. So power factor will improve. The power factor of the rotor will improve during the running conditions. The general equation of torque in any machine is given by, I have already told you, the general equation of torque in any machine is given by T is directly proportional to F1 into F2 into sin delta, but delta is the angle between the F1 and F2. Here F1 and F2 are going to be in the same direction with the same speed of omega. So the general equation of torque in any machine is equal to the torque is directly proportional to F1 into F2 into sin delta, where delta is the angle between the F1 and F2. F1 is called as the, let me assume F1 is the flux due to stator and F2 is the flux because of the rotor. They both are the same speed, which is omega. The equation of torque in DC motor is, I have already told you, torque is directly proportional to flux in the armature current. Phi is called as the flux and IA is called as the current in the armature conductor. So phi is called as the flux and IA is called as the current in the armature conductor. So in induction motor at starting, the equation of torque is, I have already told you, in induction motor at the starting, the equation of torque is, basically torque is directly proportional to RMF into I2, which is E2 I2 cos phi2. So therefore, torque is directly proportional to E2 into I2 into cos phi2. Here, E2 is the EMF induced at the standstill condition, at the starting condition. I2 is the current in the rotor at the starting condition, and cos phi2 is the power factor between the induced voltage and the induced current in the rotor. E2 is called as the starting induced voltage in the rotor. I2 is called as the starting current in the rotor, and T is called as the torque in rotor during the starting condition. So therefore, here A2 is called as the starting induced voltage in rotor. It is a per phase value. I2 is called as the starting current in the rotor, and phi2 is the phase angle between the induced voltage and the induced current in the rotor, and T is called the torque in rotor during the starting condition. Always number of poles in stator must be equal to number of poles in the slip ring rotor. Then only the rotor is going to rotate, otherwise no. The poles in slip ring rotor should be formed by coils by human being winding on them properly. I have already told you here, in case of squirrel cage rotor, by nature itself, the number of poles on the stator will be always equal to number of poles on the rotor. But in the slip ring rotor, the person has to wound the coils on the rotor. He has to make the number of poles on the rotor should be always equal to number of poles on the stator. Then only it can rotate. Otherwise, it will never rotate. So always number of poles in stator must be equal to number of poles in the slip ring rotor. Then only the rotor is going to rotate. Otherwise, no. The poles in slip ring rotor should be formed by coils by human being winding on them properly. Always the number of poles in stator must be equal to number of poles in the slip ring rotor. Then only the rotor is going to get rotated. Otherwise, no. The poles in slip ring rotor should be formed by coils by human being winding on them properly. In the case of squirrel cage rotor, automatically by God's gift, they make number of poles on rotor is equal to number of poles on the stator when the rotor rotates. I have already told you, in the squirrel cage rotor, with the help of God's grace, the number of poles on the rotor will be always equal to number of poles on the stator. Whereas in the slip ring rotor, the human being should wound the coils on the rotor, and he has to make the number of poles on the rotor should be always equal to number of poles on the stator. Whereas in the case of squirrel cage rotor, with the help of God's gift, always the number of poles on the rotor will be always equal to number of poles on the stator. So always the number of poles in the stator must be equal to number of poles in the slip ring rotor. Then only the rotor is going to get rotated. Otherwise, no. The poles in slip ring rotor should be formed by coils by human being winding on them properly. Whereas in the case of squirrel cage rotor, automatically by God's gift, they make number of poles on rotor is equal to number of poles on stator. Then only the rotor is going to get rotated. So I have already told you SM is equal to R2 by X2. Here it is fixed for a given machine. So R2 by X2 is the ratio is fixed for a given machine. So SM is called as the slip at the maximum torque is equal to R2 by X2. So whenever for a fixed machine, R2 and X2 are fixed. So this ratio is also fixed. R2 is called as the rotor resistance, and X2 is called as the rotor reactance at the standstill condition. So we can change it by adding extra resistance to rotor using slip ring induction machine. So I have already told you can change the value of R2 by adding the extra resistance to the rotor using the slip ring induction machine. If you want to change it, you have to change the value of R2. So only in the case of slip ring induction machine, we can add the external resistance to the rotor winding. Then we can change the value of R2. So we can change the value of SM. But for a squirrel cage induction motor, R2 and X2 are fixed, so SM is also fixed. But for slip ring induction motor, we can change the value of R2, so therefore SM can be varied. So SM is equal to R2 by X2. It is fixed for a machine, but we can change it by adding the extra resistance to the rotor using the slip ring induction machine. And I have already told you the maximum torque is inversely proportional to 1 by 2 X2, which is independent of rotor resistance. As you can see clearly, I have already told you the Tmax is equal to 180 by 2 by ns into E2 square by 2 into X2. As you can see clearly, the maximum torque is independent of the rotor resistance. So therefore, it is independent of the rotor resistance. So therefore, maximum torque is inversely proportional to 1 by 2 X2, which is independent of the rotor resistance. So maximum torque is always independent of the rotor resistance. So even if you change the rotor resistance, the starting torque may vary, but the maximum torque will be always constant. So by varying the rotor resistance, the starting torque can vary, but the maximum torque will be always constant. In a normal three-phase slip ring induction motor, the developed starting torque will increase with the increase in the value of the rotor resistance up to a certain value, and then decreases with the further increase in the rotor resistance. I have already told you, see, even if you increase the rotor resistance, yes, the starting torque will increase only up to a certain limit of R2. Even after increasing more than that resistance, the starting torque will decrease, because the maximum torque is going to get occur in the braking or the plugging region. So listen carefully. See, you are going to increase the rotor resistance. Yes, the starting torque will increase only up to a certain limit of R2. Even if you increase more than that R2, the maximum torque is going to get occur in the braking or the plugging region. So in that, the starting torque will decrease. So therefore, simply we can say that Yes, only up to a certain limit of increase of rotor resistance, the starting torque will increase. But if you increase more than that, the starting torque will decrease because the maximum torque is now going to occur in the braking or the plugging region. So in a normal three-phase slip-ring induction motor, the developed starting torque will increase with increase in the value of the rotor resistance up to a certain value and then decreases with a further increase in the rotor resistance because now the maximum torque is going to occur in the braking or the plugging region. Because of that only the starting torque will decrease. Whereas in the previous case, the maximum torque is going to occur in the motoring region. So in a normal three-phase slip-ring induction motor, the developed starting torque will increase with increasing the value of the rotor resistance up to a certain value and then decreases with further increase in the rotor resistance. In a three-phase induction motor, the torque developed is maximum when the rotor circuit resistance per phase is equal to slip times the rotor leakage reactance per phase at the standstill. I have already told you, in a three-phase induction motor, the torque developed is maximum when the rotor resistance per phase is equal to slip times the rotor leakage reactance per phase at standstill. I have already told you, at maximum torque, the slip at maximum torque is equal to R2 by X2. So R2 is equal to Sm into X2. So simply we can say that the rotor resistance is equal to slip times the rotor reactance at the standstill condition. So therefore, the R2 is equal to Sm into X2. Sm is called as the slip at the maximum torque. So rotor resistance is equal to slip at maximum torque into the rotor resistance at the standstill condition. This is the condition at which we are going to get the maximum torque. So in a three-phase induction motor, the torque developed is maximum when the rotor circuit resistance per phase is equal to slip times the rotor leakage reactance per phase at the standstill. Breakdown torque or the maximum torque in a three-phase induction motor of negligible stator impedance is inversely proportional to the rotor leakage reactance. I have already told you the maximum torque is inversely proportional to 1 by 2x2. So simply we can say that it is independent of the rotor. It is independent of the rotor resistance. It only depends upon the rotor standstill reactance. So maximum torque is equal to 180 by 2 pi ns into E2 square by 2 into x2. So we can see this maximum torque is only dependent upon the rotor reactance. It is independent of the rotor resistance. So maximum torque is also called as the breakdown torque. So breakdown torque or maximum torque in a three-phase induction motor of negligible stator impedance is inversely proportional to the rotor leakage impedance. Rotor copper loss is equal to S times the rotor power input. I have already told you the rotor copper loss is equal to slip times the rotor power input. I have already told you very important point. The rotor is made of lamination, so there is no core losses. Only there will be copper losses. So core loss has been absent in the rotor because the rotor is made up of with high thick insulations, thick amount of insulation. So because of this, the core loss are absent. Only copper loss are going to be present in the rotor. So rotor copper loss is equal to slip times the rotor power input. As the slip increases, we get huge losses. So always operate at the lowest. I have already told you this very important point. Basically, here whenever the slip increases, the rotor copper loss increases. So always try to operate at the low slip. I have already told you low slip is nothing but it is said to a stable region and high slip is called as the unstable region. I have already told you in detail about all these things in the induction machine concept itself. So the ratio of the starting torque by maximum torque is equal to 2 into Sm into 1 by 1 square plus Sm square. In this we can use the numerical or the percentage values in the starting torque and the maximum torque. Based on that you will always get in a Sm in numerical value. So therefore Sm is going to lie between 0 to 1. So in this we can use the numerical or the percentage values in T start or T max. Based on that you will always get Sm in the numerical values, which is 0 to Sm lies between 0 to 1. See, you can use either numerical values, either you can use the percentage values, and here you are going to get the same result, which is Sm is always going to lie between 0 to 1. Sm is called as the slip at the maximum torque. So this is basically general formula. Torque T1 at slip S1, torque Tm at slip Sm. The ratio of T1 by Tm is equal to 2 into S1 into Sm by S1 square plus Sm square. So we are going to get a torque T1 at a slip S1, torque maximum torque at maximum slip at maximum torque. So T1 by Tm is equal to 2 into S1 into Sm by S1 square plus Sm square. S1 is the slip at torque T1, Sm is the slip at the maximum torque Tm. So this is the relation that you can use. See, you can substitute the T1 as starting torque. If you are going to use the starting torque as T1, then S1 is equal to starting slip is equal to 1 because as starting NR is equal to 0, so slip is equal to 1. So if you substitute here S is equal to S1 is equal to 1 and T1 is equal to T start, you are going to get this relation. Similarly, you can use T1 as a full load, then S1 will be full load slip, then you can use the formula. So this is a general expression. T1 can be any value at a particular amount of slip S1. If the load on a squirrel cage induction motor operating on a constant voltage, constant frequency is supplied, then the power factor angle decreases, power factor increases, speed decreases, and the speed increases. If the load on a squirrel cage induction motor operating on a constant voltage, constant frequency is supplied, then the power factor angle decreases. See, I've already told you, if the load on a squirrel cage induction motor operating on a constant voltage, constant frequency is supplied, then the power factor angle decreases. See, I already told you, if you keep a load on squirrel cage induction motor, see, basically if you are going to run the induction motor, S into X2 is always lesser than X2. So as Sx2 length decreases, the power factor angle decreases, so power factor increases. Then simply we can say that as the load is increases, definitely we can say speed decreases. So definitely we can say slip is going to get increased. So whenever the load on a squirrel cage induction motor is increases, definitely we can say the speed decreases, so slip increases. So if the load on a squirrel cage induction motor operating on a constant voltage, constant frequency is supplied, then power factor angle decreases, power factor increases, speed decreases, and the slip increases. So whenever you increase the load on a squirrel cage induction motor, definitely the speed decreases, so slip increases, the rotor speed decreases, slip increases, and also, so this that you are going to get here. Three-phase induction motor is loaded from no load to rated load, then there is an improvement in the power factor. The torque increases almost in proportional to the slip, and the air gap flux is constant. I already told you very important point. Suppose as whenever a three-phase induction motor is loaded from no load to full load, no load to rated load or full load, then there is an improvement in the power factor. I already told you. See, there is the value of S is going to get less than 1. So therefore simply S into X2 is less. So therefore the power factor angle decreases. So power factor increases. So therefore I already told you, in a stable region the torque is directly proportional to slip. As the slip increases, the torque is also increases in a linear fashion. The torque increases almost in proportional to the slip, and the air gap flux is almost constant. So as a three-phase induction motor is loaded from no load to full load, no load to rated load or full load, then there is an improvement in the power factor. The torque increases almost in proportion to the slip, and the air gap flux is almost constant. Mechanical loss and the rotor core loss are rotational losses which are not included in the equivalent circuit diagram of induction motor. See, mechanical loss and the rotor core loss. I have already told you the rotor core loss. Rotor core loss are neglected. I have already told this important point, and the mechanical loss. So these two losses, these are the rotational losses. The rotor core loss plus mechanical loss. I have already told you the rotational losses means combination of iron loss and mechanical loss. So mechanical loss and rotor core loss is called as rotational losses, which are not included in the equivalent circuit diagram of induction motor. So these two losses that we have not included in the induction motor equivalent circuit diagram, which is the rotor core loss and also the mechanical losses. Mechanical losses means it is also called as the friction and windage losses, and the rotational losses means it is a summation of the mechanical loss and also the iron loss. So here mechanical loss and the rotor core loss, these are called as the combination of these two is called as the rotational losses, which are not included in the equivalent circuit diagram of induction motor. In order to find the equivalent circuit parameters of the induction motor, these tests are performed. They are called as a no load test and a block rotor test and a DC test, and all these are called as a non-loading test. I have already told you very important point. See, if you want to figure out all the parameters of the equivalent circuit diagram of an induction motor, then we have to perform the no load test. So with the help of no load test, we can figure out the shunt branch parameters, and with the help of block rotor test, we can figure out the series branch parameters, and with the help of DC test, we can figure out the armature resistance, RA, we can easily figure out. So simply we can see it is also called as the DC test means we are going to find what is the resistance of the stator winding. The resistance of the stator winding we can figure out. So and all these are called as a non-loading test. So all these are called as a non-loading test. So therefore simply we can say that in order to find the equivalent circuit parameters of induction motor, these tests are performed. They are called as a no load test, block rotor test, DC test, and all these are called as the non-loading test. I have already told you the open circuit test of transformer is equal to no load test on induction motor. Similarly, the short circuit test on the transformer is equal to block rotor test on the induction motor. And DC, by using the DC test, we are going to find what is the resistance of the stator coil, and all these are called as the non-loading tests. So with the help of no load test, we are going to figure out the shunt branch parameters, and with the help of block rotor test, we are going to find the series branch parameters, and with the help of DC test, we are going to find the resistance of the armature or simply we can say stator coil. So transformer is a singly exited magnetic system. I've already told you transformer is a singly exited magnetic system, whereas synchronous motor is a doubly exited magnetic system, whereas relay is also a singly exited magnetic system. So transformer is a singly exited magnetic system, relay is a singly exited magnetic system, even the induction motor is also singly exited magnetic system, whereas the synchronous motor is a doubly exited magnetic system. Synchronous motor and the synchronous generator both are called as the doubly exited magnetic system. So this is a very important point. Transformer is basically a singly exited magnetic system, relay is a singly exited magnetic system, and also the induction machine is also a singly exited magnetic system, whereas a synchronous motor is a doubly exited magnetic system. See, singly excited means only one winding is being excited. Doubly excited means both the windings have been excited. That is the meaning of this one. Single excitation means only with the only one coil. If you are going to give the excitation, this called as the single excitation. Double excitation means if you go for the two coils, if you are going to give the excitation, this called as the double excited magnetic system. The starting methods of induction motors are the direct online starting, stator resistance or reactor start, auto transformer start, star delta start, and rotor resistance start. So these are the different methods of starting these are called as the starting methods of the induction motors, which are the direct online starting. Direct online starting means the stator is in the delta fashion always. Stator resistance or reactance start, auto transformer start. Star delta means initially we are going to assume the stator is in a star connection, and then we are going to convert into delta later, and the rotor resistance start. So these are the different methods by which we are going to go for the starting methods of the induction motor, which are the direct online means always the stator of the, I already told you, the stator of the induction machine can be either star or delta, but always the stator of the synchronous machine will be always in the star connection only. Similarly, the rotor of the induction machine should be always connected in the star fashion only. I have already told you these important points. So simply now we can say that here the starting methods of induction motors are the direct online starting, stator resistance or reactor start, and the auto transformer start, and the star delta start, and the rotor resistance start. Three-phase induction motor and the DC motors are self-starting methods. I have already told you three-phase induction motor and the DC motors are self-starting motors. These are basically self-starting motors, not methods. It's a wrong one here. So three-phase induction motor and DC motors are called as the self-starting motors. I have already told you that basically three-phase induction motor and the DC motors are self-starting motors, whereas the single-phase induction motor and the three-phase synchronous motor are not self-starting motors. So three-phase induction motor and the DC motors are self-starting motors, whereas the single-phase induction motor and the three-phase synchronous motor are non-self-starting motors. So let me tell you what is going to happen during the starting process. So during starting, suppose during starting we are going to give the rated supply voltage to the stator. So because of this, the RMF is going to rotate at a speed of synchronous speed ns. Then because this is going to cut the rotor, so rotor is going to get some EMF induced, which is called as a E2. These are called as a per phase induced voltage. It's a very huge value. During the starting process. So very huge value. So therefore, what is the value of current? I2 is equal to E2 by R2 plus JX2. As I already told you, at the starting condition, the NR is equal to 0. So NR is equal to 0 means slip is equal to 1. So S is equal to 1. So we are going to get a huge amount of current, because as E2 is very high, so it is also very huge current. Then I2 by K is also a very huge value. It's a very huge value. Means I2 by K is nothing but it's a current reflected to the stator. I2 by K is called as a current reflected to the stator. So therefore, the current in the rotor is very high, and the stator current is also very high. So motor starts, but now E2 becomes SE2, very low. So therefore, whenever the motor starts, the slip is going to get occur. So now E2 is going to become very less, S into E2, very low value. And I2 becomes I2 dash, even very low, because if the EMF is less, then I2 is also very less. This time interval is called as the inrush time. So whatever this time is called as the, initially we have large amount of E2, large amount of I2, but suddenly when the motor started, there is a small amount of E2, a small amount of current I2. So this interval is called as the inrush time. So this small interval is called as the inrush time. So this is a serious problem for large rating machine, but nothing happens for small rating machines. So we use starting methods to reduce the sudden dip of voltage and current in the rotor. See, this is a very serious problem for the large rating machine, but not for the small rating machines. So we have to use the starting methods to reduce this sudden dip of voltage and current in the rotor. So we decrease the supply voltage. So by using the starting methods, we have to decrease the supply. We will decrease the supply voltage. As we decreases, then definitely the flux decreases. So therefore, if the flux decreases, definitely E2 decreases. If E2 decreases, I2 decreases. Then definitely as I2 decreases, the starting current also decreases. So this is the things that you always have to remember this one. So therefore, during starting I already told you E2 and I2 are very high. So whenever the motor starts, E2 and I2 are very less. So there is a sudden dip of voltage and current in the rotors. So this time is called as the ingress time. So we have to see, this is a very serious problem for the large rating machines, but nothing happens for the small rating machines. So definitely by using the starting methods, we need to reduce the sudden dip of voltage and current in the rotor. So all these starting methods are going to reduce the supply voltage. So therefore the flux decreases. So E2 decreases, I2 decreases. So therefore the starting current also decreases. So this is the basic function of the starting methods. All the starting methods are going to reduce the supply voltage. So therefore simply we can say that all these are the phase values. As we are going to decrease the supply voltage, the flux decreases, E2 decreases, I2 decreases, and starting current decreases. So finally, let me give a conclusion about this concept. So during starting, when we are going to give a rated voltage, definitely whatever the flux is rated and it is going to rotate at a speed of ns RMF. See, whenever this rated flux is going to cut the rotor, it is going to give a induced EMF E2 very huge value, and the rotor current is equal to E2 by R2 plus JX2, and starting NR is equal to 0, so S is equal to 1, so you are going to get a huge amount of current, and the current referred to the stator is also very huge value. So motor starts, but now E2 becomes SC2 very low value, and I2 becomes I2 dash very low value. So whenever the motor starts, slip is going to come, so SC into it is very less and I2 dash is also very less. So this time interval is called as an ingress time. So this time interval is called as an ingress time. So this is a very serious problem for the large rating machine, but nothing happens for small rating machines. So this is a very huge problem for large rating machines, but nothing happens for small rating machines. So we have to use the starting methods to reduce this sudden dip of voltage and current in the rotor. So by the starting methods, our basic agenda is to reduce this sudden dip of voltage and current in a rotor. So we have to decrease this time. We have to decrease this time to a very less value. So all the starting methods are going to reduce the sudden dip of voltage and current to a lower values in the rotors. So all the basic starting methods are going to reduce the supply voltage. As the supply voltage reduces, whatever the flux in the air gap is going to get decreased, U2 is going to get decreased, I2 is going to get decreased, and the starting current is also going to get decreased. So all these are going to get reduced. Now the dip is going to get further decreases. So therefore we can say this is the basic agenda of all the starting methods. I have written again here. If you give a rated voltage, the flux you are going to get rated flux, then you are going to get E2, and then you are going to get I2, then you are going to get I2 by K, and this is called the starting current. Suppose if you do X times of V, the flux becomes X times of phi, then EMF is going to become X times of E2, and the rotor current is going to become X times of I2, and the stator current referred to stator is called as X into I2 by K, and this current is also become very less. So if you reduce the supply voltage, all these things are reduced by a factor of X. So ISC is for the starting current, so X is always less than 1, because we are going to reduce this voltage. If we reduce the voltage, all the things have been reduced by a factor of X. So this is the basic agenda of all the starting methods. So whenever you decrease the value of voltage, all the things have been decreased by a factor of X. So if you give a rated voltage, you are going to get a rated flux. It is called as the EMF induced in the rotor. I2 is the current induced in the rotor. I2 by K is called as a current which is referred to the stator coil, and this is called starting current. So if you reduce the voltage by factor of X, phi is also reduced by factor of X, E2 is also reduced by factor of X, I2 is also reduced by factor of X, I2 by K is also reduced by factor of X, and ISC is also reduced by factor of X. ISC is for the starting current, and X is always less than 1. So all the starting methods aim is to decrease the starting current and increase the starting torque. So this is a very important point. Listen carefully. All the starting methods aim is to decrease the starting current and increase the starting torque. So this is the basic function. This is the basic function of all the starting methods. All the starting methods are going to reduce the voltage. So therefore, we can decrease the starting current, but we have to increase the starting torque. So all the starting methods aim is to decrease the starting current and increase the starting torque. It's a very important point that you always have to remember. All the starting methods of this induction motor basic functions is to reduce the starting current and increase the starting torque. So this is the basic agenda or basic aim of all the starting methods. So all the starting methods aim is to decrease the starting current with increase in the starting torque. A three-phase induction motor requires a starting methods or starter because the induced secondary voltage and hence the currents in the windings are abnormally high during the starting. I've already told you a three-phase induction motor requires a starting methods or starter because the induced secondary voltage and the hence the currents in the windings are abnormally high during the starting. So I've already told you during the starting whatever the EMF induced in the rotor and whatever the current induced in the rotor are very high. So because of this reason only we need the starting methods are also called as the starters. So these are the starters which are required. In the DC machines also we have learned initially at the starting IA is very high, so we have to reduce it to a normal value, to a safe value with the help of starter. Similarly here also we are going to use the starting methods of the starter. But by this we are going to decrease the EMF induced in the rotor and the current induced in the rotor at the starting. So with the help of these things, with the help of the starting methods or the startup, we are going to reduce the basically whatever the EMF induced in the rotor and whatever the current induced in the rotor to a normal value. So with the help of this starting methods of starters. So a three-phase induction motor requires a starting methods of starter because the induced secondary voltage and hence the currents in the windings are abnormally high during the starting. As per load requirement, we must change speed that is below the rated speed or above the rated speed. But unfortunately, no method in induction motor speed control will give speed variation like shunt motor. As per load requirement, we must change speed that is below the rated speed or above the rated speed. But unfortunately, no method in induction motor speed control will give speed variation like shunt motor. I already told you all the DC motors have experienced speed control characteristics than any other motor. So based on the load demand, sometimes the load demand requires huge amount of speed, or sometimes the load demand can require less amount of speed. All these things that we need to give as per the load demand. But in the induction motor, the speed control is not as good as compared to DC shunt motors, or simply we can say DC motors. So as per the load requirement, we need to give whatever the speed the load is required. It may ask you to give load speed, or sometimes it may ask to give high speed. So based on that, we have to change the induction motor speed to the required level of asked by the load. But unfortunately, there is the speed control techniques, the speed control mechanism of induction motor is not so good when compared to a DC motors, or simply we can say DC shunt motor. As per the load requirement, we must change speed that is below the rated speed or above the rated speed. But unfortunately, no method in induction motor speed control will give variation like shunt motor. As I already told you, NR is equal to NS into 1 minus S. So NR is going to depend upon the NS and also slip. See, you can see clearly from this relation, NR is a function of NS and S. So NR is going to depend upon the NS and also S. NS is equal to 120 F by P. As you increase the frequency, NS increases, and as you decrease P, again NS increases. Either you increase frequency, then you will increase NS. Either you decrease P, then you are going to get increase in NS. As whenever NS increases, NR is also increases. So therefore, torque is equal to 180 by 2 by NS into S into square R2 by R2 square plus SX2 whole square. This is the general equation of the torque in a three-phase induction motor. I have already told you here, torque is directly proportional to S into V square by R2 for low. We can say that basically this is called as the low slip region. So this is called as a low slip region. Low slip region means simply this is stable. It is stable. In a stable, I have already told you S is a very less value, because in a stable region S is a very less value. So S into X2 is neglected. So therefore, here R2 cancels. We are going to get S into V square by R2, because V2 is proportional to E1 and E1 is proportional to V, so we are going to get S into V square by R2. As you can see clearly, let me assume the rotor resistance is constant, so torque is directly proportional to S into V square. This is called as a voltage control. So this is called as a voltage control. If you increase voltage, the torque is also going to get increased. So this is called as a voltage control. Suppose again S is directly proportional to S V square by R2. So suppose let me assume V is a constant, then definitely T is directly proportional to S by R2. So that's for the resistance control. So if you decrease R2, the torque is also decreasing at the running conditions. I am speaking about at the running conditions. At the starting conditions, as you increase R2, the torque increases. But during the running conditions, as you increase R2, the torque will decrease. As you can see clearly from this equation itself. So therefore, in the running conditions, if you increase R2, the torque decreases. But during the starting conditions, if you increase R2, the torque increases. I have already told you this very important point. So during the starting conditions, if you increase R2, yes, torque increases. But during the running conditions, you can see clearly from this equation, as you increase R2, the torque will decrease. So this is the torque is a function of V, it is called the voltage control, and torque is a function of R2, so it is called as a resistance control. So now we will discuss another important point. So from stator side, the speed control techniques are voltage control, frequency control, the pole changing, and the stator resistance. So from stator side, the speed control techniques are the voltage control, frequency control, pole changing, stator resistance. From rotor side, the speed control techniques are the rotor resistance control, slip over recovery, and the cascading of tandem. So these are the different types of speed controls from the stator and also from the rotor. So from stator, we can say that from stator side, the speed controlling techniques are called as the voltage control. I have already told you, if you change the voltage, then definitely we can change the speed of the rotor. Frequency control, I have already told you, if you change the frequency, NS is going to get changed, so NR is also going to get changed. Pole changing means if you change the poles, NS is going to get changed, so therefore NR is also going to get changed. Stator resistance control. Stator resistance control, I have already told you, if you change the R2, torque is going to get changed, so speed is also going to get changed. So therefore, we can say that from stator side, the speed control techniques are the voltage control. So if you change the voltage, then torque is going to get changed and speed is also going to get changed. Frequency control, if you change the frequency, then NS is going to get changed, so NR is also going to get changed. Pole changing, whenever you change the poles, the NS is going to get changed, so NR is also going to get changed. Similarly, stator resistance, if you change the stator resistance, torque is going to get changed, so whenever torque changes, the corresponding speed is also going to get changed. So these are different methods. From the stator side, we can control the speed. So voltage control, frequency control, pole changing, and stator resistance. From rotor side, the speed control techniques are the rotor resistance control. I have already told you rotor resistance. When you change the rotor resistance, definitely we can say whenever you change the rotor resistance, torque changes, so speed changes. Slip power recovery and the cascading of tandem. So these are the three methods from the rotor side that you can control the speed. So 4 methods from the stator and 3 methods from the rotor. So from stator side, the speed control techniques are the voltage control, frequency control, pole changing, and stator resistance. Whereas from the rotor side, the speed control techniques are the rotor resistance control, slip power recovery, cascading, or tandem. In a frequency control, I have already told you E is equal to 4.44 N1F B1 BMA, and BM is directly proportional to voltage by frequency. Then you can see clearly voltage by frequency. If V is equal to constant, and frequency increases, then definitely maximum flux density decreases, and also EMF induced decreases. As you can see clearly, as BM decreases, E also decreases, and also the torque is also going to get decreased, because torque is a function of E2, direct function of E2. As E2 decreases, torque also decreases. So in a frequency control, E is equal to 4.44 F N1 BMA, as BM is directly proportional to V by F. Whenever the supply voltage is equal to constant and frequency increases, so BM decreases. As the BM decreases, E decreases. As E decreases, torque decreases. So in a frequency control, E is equal to 4.44 NF. Actually, it is NF phi n. Phi n is nothing but BM into A. So therefore, here N1 we are going to take. N1 is called the stator coil per phase. The stator coil per phase turns. So BM is directly proportional to supply voltage by supply frequency. If the supply voltage is a constant and the frequency increases, then BM decreases, then E decreases. I have already told you torque is a function of E, because T is equal to 180 by 2 pi ms into S E2 square R2 by R2 square plus S x2 square. As you can see, clear torque is a function of E2. So therefore, as E decreases, then definitely torque is also decreases. Pole changing method. In pole changing method, as you can see clearly, in a pole changing method. So in a pole changing method, as pole changes, NS changes, so NR also changes. I have already told you in a pole changing method. This is a frequency control means by changing the frequency, you are going to change the torque, so NR is also going to get changed. In pole changing method, as pole changes, ns changes, so nr also changes. These things I already told you. In the pole changing method, if you change the poles, ns changes, so nr is also going to get changes. See, constant load means it requires constant torque. So whenever you listen to constant load, it means that it requires a constant torque. So whenever a constant load means it requires a constant torque. So whenever you listen a constant load, it means that it is a constant torque. So that load is actually really a constant torque. So constant load means it requires a constant torque. So slip speed means it is a difference between the synchronous speed and the rotor speed. Ns minus nr is equal to s into ns. Here you can use either n or nr, both are same. N or nr both are same. It is rotor speed. So slip speed is equal to difference between the synchronous speed and the rotor speed, which is ns minus nr is equal to s into ns. Under variable frequency operation of three-phase induction motor, air gap flux is kept constant by adjusting the motor voltage. For constant air gap flux, machine develops the same torque when the slip speed is kept constant. So listen carefully. Under variable frequency operation of three-phase induction motor, air gap flux is kept constant by adjusting the motor voltage. For constant air gap flux, the machine develops the same torque when the slip speed is kept constant. So what I am trying to say basically here it is basically a V by F control method. It's a V by F control method. If you want the constant air gap flux, then the machine, for a constant air gap flux means V by F control, then definitely the machine is going to get the same torque whenever the slip speed is kept constant. If the slip speed is kept constant, then only the torque is going to get same. So let me here listen carefully. I have already told you here in a stable region, as I have already told you, torque is directly proportional to S V square by R2 into F. In the stable region, torque is directly proportional to S V square by R2 into F. So if you do the T2 by T1, so T2 by T1 is equal to S2 by S1 into V2 by V1 whole square into F1 by F2 by that relation. I have already told you Bm is nothing but Bm is directly proportional to V by F. As here, suppose let me assume V is decreasing, so V by 2 and F by 2, so both is the constant, again V by F. So Bm is always constant because we are changing the voltage and also changing the frequency, but the ratio is always constant. So constant flux density means constant flux. As the flux density is a constant, flux is also constant. So it's a constant V by F control, or simply we can say constant V by F control. So I want the torque to be same. So therefore same torque means the ratio is 1. So now if you solve this one, S2 by S1, let me assume V2 is nothing but V1 by 2 or V1 by 2 and F2 is nothing but F1 by 2, because we are going to keep the same amount of, the ratio of Vm is same. So if you solve this one, we are going to get S2 is equal to 2 into S1. So S1 into NS1 is equal to S2 into NS2. So S1 into NS1 is equal to S2 into NS2 because this is called the slip speed. So slip speed for the first case is equal to slip speed for the second case. If you want the torque to be same under the V by F control. So under the V by F control, if you want the torque to be constant, then definitely the slip speed should be always equal. S1 into NS1 is equal to S2 into NS2. So under variable frequency operation of a three-phase induction motor, air gap flux is kept constant by adjusting the motor voltage. Then for constant air gap flux, machine develops the same torque whenever the slip speed is kept constant. I have already told you Bm is directly proportional to V by F. If Bm is a constant, then definitely torque is also constant. So let me assume initial voltage is V and initial frequency is F. So we are going to change the V and F in such a manner the ratio is always constant. Let me assume V by 2 and F by 2. So I have already told you in a stable region torque is directly proportional to S V square by R2 into F. So here R2 we are going to neglect, only S V square by F we are going to take. So T2 by T1 is equal to S2 by S5 into V2 by V1 whole square into F1 by F2. As V1 is equal to V and F1 is equal to F. So V2 is equal to V1 by 2 and F2 is equal to F1 by 2. So if you solve this one, we are going to get S2 is equal to 2 into S1. So S1 into NS1 is equal to S2 into 2S2, because S2 is equal to 2 into S1 and NS2 is nothing but 120 F by 120 F2 by P2. Here P, so therefore F2 is nothing but simply here F by 2. So therefore simply 2 to cancel, so we are going to get S1 into NS1 is equal to S2 into 2S2. So S2 into 2S2, S2 into NS2, so therefore this part the slip speed is kept constant. So finally I can say that if you want the air gap flux to be constant, at the air gap flux constant, then definitely, or simply V by F control, then if you want the same torque, then definitely slip speed should be always kept constant. So under variable frequency operation of three-phase induction motor, air gap flux is kept constant by adjusting the motor voltage. For constant air gap flux, machine develops the same torque whenever the slip speed is kept constant. In order to control the speed of a slip ring three-phase induction motor through injected voltage in its rotor circuit,
this voltage and the rotor voltage should essentially be of the same frequency. In order to control the speed of a slip ring, three-phase induction motor through injected voltage in this rotor circuit, this voltage and the rotor voltage should be essentially of the same frequency. Whatever the injected voltage frequency and the rotor induced EMF frequency should be same, then only we can control the speed of the rotor. So listen carefully. In a slip ring induction motor, if you want to control the speed of the rotor, definitely whatever the EMF induced in the rotor frequency and the injected voltage in the rotor frequency should be same, then only we can control the speed of the rotor. In order to control the speed of the slip ring three-phase induction motor through injected voltage, this rotor circuit, this voltage and the rotor induced voltage, it is basically rotor induced voltage should be essentially of the same frequency. In order to control the speed of a slip ring three-phase induction motor through injected voltage in this rotor circuit, this voltage and the rotor induced voltage should be essentially of the same frequency. So if you want to control the rotor speed of a slip ring induction motor, whatever the injected voltage frequency and the whatever the rotor injected voltage frequency and the rotor induced voltage frequency should be same, then only we can control the rotor speed. Under VBF control of induction motor, the maximum value of the developed torque remains constant over a wide range of speed in the subsynchronous region because the magnetic flux is maintained almost constant at the rated value by keeping the ratio V by F constant over the considered speed range. I've already told you, whenever the V by F ratio is a constant, the maximum torque is always constant because maximum torque is equal to, as I've already told you, which is 180 by 2 pi ns into e2 square by 2 into x2, as e2 is directly proportional to e1, e1 is directly proportional to v, and x2 is directly proportional to f, and ns is directly proportional to f. So finally, torque is directly proportional to v by f whole square. As v by f is a constant, so maximum torque is also constant. So this is the thing that you can easily analyze from this one. So under v by f control of induction motor, the maximum value of the developed torque remains constant over a wide range of speed in the subsynchronous region because the magnetic flux is maintained almost constant at the rated value by keeping the ratio V by F constant over the considered speed range. As V by F is a constant, maximum flux density is a constant, so flux is also constant. So under V by F control of induction motor, the maximum value of the developed torque remains constant over a wide range of speed in the subsynchronous region because the magnetic flux is maintained almost constant at the rated value by keeping the ratio V by F constant over the considered speed range. I already told you in a V by F ratio control, the maximum torque is always constant, and if you want the same torque, then definitely slip speed should be always same. The braking of induction motor is done by three methods. They are called as the dynamic braking, plugging, and the regenerative braking. So these are the same methods for even DC motors also. The braking methods of DC motors also same. It is the dynamic method, plugging method, and the regenerative method. So the braking methods of the induction motor is done by three methods. They are called as the dynamic method, plugging method, and the regenerative braking. So these are the same methods even for the DC machine also. DC motors also same methods. The braking methods of the DC motors and the induction motors are same, which are called as the dynamic, plugging, and the regenerative. In plugging mode, just interchange the supply to any two phases. In the plugging mode, just interchange the supply to any two phases. See, basically in the induction, see in the DC motor I have already told you, plugging is just you have to interchange the terminals of the armature terminals, then you are going to get a reverse torque. Similarly here, in the plugging method, in the induction motor, you have to interchange the supply of any two terminals, then you are going to get a reverse RMF. If you get a reverse RMF, then definitely, so therefore the speed is going to get decreased and it is going to come stationary. But if you then at that, whenever the speed is going to become zero, at the time you have to remove the supply, otherwise it is going to rotate in the reverse direction. In dynamic braking, when input is equal to AC, three-phase supply, we get RMF, and now rotor rotates. Now join B and C and give DC supply to stator. So DC flux the rotor, so EMF induces the rotor. So this torque opposes the motional speed of rotor, but this takes more time than the plugging method. So basically now in dynamic braking of induction motor, see in dynamic braking, when input is equal to AC, three-phase supply, we are going to get RMF, and now rotor rotates. Now join B and C and give DC supply to stator. So DC flux cuts the rotor, so EMF induced in the rotor. So this torque opposes the motion of the speed of rotor, but this takes more time than plugging method. I have already told you basically as a stator. Initially I am going to give a three-phase supply, So we are going to get RMF and the rotor is going to get rotate. I want to make it to come 0 speed in a small time. So now let me assume I'm going to use the dynamic braking. Dynamic braking means I need to short circuit this B and C and give a DC supply across the B and this common terminal. Whenever I give a DC voltage, whatever the flux you are going to get is DC flux. This DC flux is going to cut the rotor. As the rotor is rotating, but the flux is a constant. So then also we are going to get a EMF induced in that one. See, whenever the flux is a constant and rotor is rotating, this is called dynamically induced EMF. This EMF is going to produce the torque which is opposite to the rotor. So the rotor is going to get this, we can say it is going to decrease its speed and it is going to come to a stationary. So but whatever the time which is here to come 0 speed, it is more than the plugging method time. So we can say plugging method is somewhat faster when compared to dynamic braking. To speed between the rotating magnetic field and the rotor is 0, thereby eddy current loss is equal to 0. I already told you whenever the relative speed between the rotating magnetic field and the rotor is 0, then definitely thereby eddy current loss is equal to 0. So therefore, if NR is equal to NS, then there is no relative speed, so eddy current loss is equal to 0, so no torque is going to get produced. So listen carefully. Whenever the NR is equal to NS, so slip is equal to 0. Whenever the slip is equal to 0, torque is equal to 0. So we can say that whenever NR is equal to NS, there is no relative speed difference between the RMF and the rotor. So simply we can say the relative speed between the RMF and the rotor is equal to 0, thereby eddy currents will 0, because as there is no relative flux, then definitely no flux cutting. So therefore simply we can say EMF is equal to 0, so current is also 0, so eddy current loss is also 0, so torque is also equal to 0. The rotor core is made up of solid steel forging of nickel, chromium and molybdenum. So rotor core is made up of solid steel forging of nickel, chromium and molybdenum. So whatever the rotor core is basically made up of solid steel forging of nickel, chromium and molybdenum. So rotor core is made up of solid steel forging of nickel, chromium and molybdenum. In the cylindrical pore rotor core itself will do function of damper winding. I have already told you, in the cylindrical pore rotor core itself will do the function of a damper winding. So rotor core is made up of solid steel forging of nickel, chromium and the molybdenum. In the cylindrical pole rotor core itself is going to do a function of the damper winding. I have already told you the important functions of the damper winding in the synchronous machine. So in the damper winding of the function of damper winding in synchronous motor is to prevent the hunting, and also it is going to provide the starting torque. Whereas in the synchronous generator, the function of the damping winding is to suppress the negative sequence components of fluxes, and also so only one function is done by the damper winding in the case of the synchronous generator. Whereas in case of synchronous motor, the damper winding does two functions, whereas in the case of synchronous generator, damping winding does only one function. I have already told you everything in the detailed manner. So rotor core is made up of solid steel forging of nickel, chromium and molybdenum, and in the cylindrical pole rotor core itself will do function of damper winding. So in regenerative braking, whenever the N is greater than NS, so then definitely slip is equal to negative, because regenerative braking means the rotor speed should be always greater than synchronous speed. Then definitely slip we are going to get negative. So whenever slip is negative, the torque is also negative, because torque is directly proportional to slip. So torque is also negative. As torque is negative, EMF induced is also negative, because S into E2. So E2 is also negative. So current I2 is also negative. So therefore I2 dash by K is also negative. So therefore simply we can say that the rotor speed will decrease. I have already told you the regenerative braking means whenever the rotor speed is greater than synchronous speed during the hauling conditions, whenever the train is reaching downward, sometimes the speed can be greater than synchronous speed. So slip is equal to negative. So whenever the slip is negative, torque is also negative, and negative torque is going to oppose the motion of the rotor. So therefore, it will never decrease the speed. It will never decrease the speed, but it will try not to increase the speed more than the particular value. It will always try to decrease the NR less than N. It will try always to make NR less than NS, but it will never make the torque to become 0. So therefore, simply we can say that as torque is the negative, it is going to try to oppose the increase of speed in further and further more. So it is trying to oppose the increase of speed further more. As torque is equal to negative, it is also negative, because S into it is negative. I dash is also negative. I dash by K is also negative. So speed will decrease. So simply we can say the speed will decrease, but it will never become zero. With the help of regenerative braking, it will never make speed to become zero, but it will only decrease the speed less than ns. But it will never increase more and more speed when compared to ns. Plugging means basically, plugging means making machine to off. It asks more electrical power and mechanical power to stop rotation. So plugging means I've already told you. So plugging means plugging means here making machine to off. It asks more, means making machine to off. It makes more electrical power and mechanical power to stop rotation. I've already told you plugging means basically we need to make the machine to off. Whenever you change any two terminal supply, definitely you are going to get a RMF in the reverse direction. So whenever the rotor speed is becoming zero, just you have to make the supply to off. So plugging means making machine to off. It asks more electrical power. It basically asking the more electrical power and mechanical power to stop rotation. So it is going to ask more electrical power and mechanical power to stop the rotation. So during this plugging, a huge amount of electrical power, because RMF is opposite to rotor. So whatever the overall energy is going to induce in the rotor, so whatever the overall energy is going to consume by the rotor, so rotor should have this much amount of capability of accepting this rotation. So the rotor should have this much amount of capacity to accept that energy. So therefore simply it is asking more electrical power and mechanical power to stop the rotation. An induction generator takes reactive power from the mains and supplies active power to mains. I have already told you, induction generator accepts the reactive power, so therefore it can produce the flux and delivers the active power. If you connect an induction generator to a bus bar, it always accepts the reactive power to produce the flux and it always generates the active power to the bus bars. An induction generator takes the reactive power from the mains and supplies active power to mains. The voltage actually used for setting up the usual flux in the air gap of a three-phase induction motor is lesser than the applied voltage. So whatever the voltage actually used for setting up the useful flux in the air gap of a three-phase induction motor is always lesser than the applied voltage. Yes. See, if you give an applied voltage, some of the voltage drop is going to occur in the resistances. The remaining voltage, with the remaining voltage only we are going to produce the useful flux. So therefore, the voltage actually used for setting up the usual flux in the air gap of a three-phase induction motor is lesser than the applied voltage, because in the applied voltage some of the voltage is dropped in the resistance and the remaining voltage is only used for setting up the useful flux. The third harmonics in flux is not responsible for any torque production but only produces losses. I have already told you, third harmonics are called as a zero component harmonics because they never have the rotation. See, if there is no rotation, means no torque. So therefore simply we can say that as they have no rotation, definitely there is no torque production but only produces losses, because as these are the fluxes, definitely whenever the rotor is rotating, this flux is going to cut the rotor. So therefore it is called as the dynamically induced EMF is going to get produced. So currents are going to get produced. It is called as the eddy current losses. So third harmonics in flux is not responsible for any torque production but only produces the losses. I have already told this important point, because these are zero sequence components, they will never rotate. So because of this only we can say that they never produce the torque but they are going to produce the losses. Crawling effect is occur only at the starting condition. So to remove this, we should go for short pitch winding, skew the slots or semi-closed slots. So because of all this, flux distribution is sinusoidal, so no crawling effect. See, I have already told you crawling means running at very slow speed, because the induction motor is assumed that whatever this rotor speed is equal to ns by n. Whenever the rotor speed is equal to ns by 7, they may assume that it is called a stable region, but actually it is not, because of the non-sinusoidal flux. In the air gap, whenever the flux is non-sinusoidal, harmonics are going to get present there. So because of the seventh harmonic is always dominant. So because of this only, the rotor speed is nearly equal to ns by 7. At this low speed, the overall characteristics are going to get changed. The torque and speed characteristics are going to get changed. At this low speed, the rotor may think that it is a stable region, but actually it is not, because of the non-sinusoidal flux distribution. So if you remove this one, definitely this crawling effect is absent. So by using some things, we have to remove this non-sinusoidal flux. So by using these things, which is called as by using the short pitch winding or either screwing the slots or semi-closed slots, with the help of these things, we can say that we can remove the non-sinusoidal flux distribution. So we can make the pure sinusoidal. So now the crawling effect is eliminated. So crawling effect occurs only at the starting condition. So to remove this, we should go for the short pitch winding or screwing the slots or the semi-closed slots. So because of all this flux distribution is sinusoidal, so no flux, no crawling effect. So crawling effect is only occurs at the starting condition. So to remove this, we should go for the short pitch winding of the rotor or go for the screwing the slots or basically semi-closed slots. So because of all these things, flux distribution is sinusoidal, so now no crawling effect is going to get occur. The torques produced by these effects is called as the parasitic torque. So by screwing these effects decreases and so magnetic humming decreases. I already told you with the help of screwing, we are going to reduce the crawling and clogging. But one more important point is we are going to decrease the efficiency also, because whenever the screwing, by screwing the rotor bar length increases, as rotor bar length increases, the resistance increases, so losses increases, the rotor copper loss increases, so therefore simply we can say efficiency decreases. So whatever the torques produced by these effects is called as a parasitic torque. So because of these harmonics, whatever the torque is producing except the fundamental, whatever the torque produced by the remaining harmonics is called as the parasitic torque. So by screwing these effects decreases and so by magnetic humming decreases. So whenever you go for the screwing, all this crawling and clogging effects have been removed because the flux is pure sinusoidal. So therefore magnetic humming, the noise is also going to get decreased. All these things are decreased if you go for the screwing, semi-closed slots or the short pitch winding. So these are the very important points that you always have to understand. So crawling effect occurs only at the starting condition. So to remove this, we should go for the short pitch winding or the screwing the slots or the semi-closed slots. So because of all this, the flux distribution is sinusoidal, so no crawling effect. The torque produced by these effects is called as the parasitic torque. Means the torque produced by the harmonics is called as the parasitic torque. So by screwing the slots, these effects have been decreased. So humming also, so magnetic humming is also going to be decreased. Squirrel cage has better running characteristics than the slip ring induction motor. I have already told you the squirrel cage has the better running characteristics, but the starting characteristics are better for the slip ring and the running characteristics are better for the squirrel cage. So squirrel cage has the better running characteristics than slip ring, or simply we can say the slip ring has the better starting characteristics than the squirrel cage. So inversely, squirrel cage has the better running characteristics than the slip ring induction motor. Whereas the slip ring induction motor has the better starting characteristics than squirrel cage. Similarly, squirrel cage has better running characteristics than the slip ring induction motor. The rotor of a 4-pole 3-phase squirrel cage induction motor is replaced by a 3-phase 4-pole wound rotor. When fed with normal supply, the machine will run at slightly lower than the normal speed. The rotor of a 4-pole 3-phase squirrel cage induction motor is replaced by a 3-phase 4-pole wound rotor. When fed with normal supply, the machine will run at slightly lower than normal speed. See, what I'm trying to say is basically, see, both the ratings are same, 3-phase and 4-pole. But the only thing is here, in this first case is squirrel cage induction motor, and the second case is called as the spring rotor. So let me assume which speed is lesser, because I've already told you the running characteristics of the slip ring induction motors are lesser. So as the characteristics is lesser, the speed is also lesser. So simply we can say that the running characteristics of the squirrel cage induction motor is very good, so its speed is also very good. But this one is very less, so speed is very less when compared to squirrel cage induction motor. So I've already told you the running characteristics of the squirrel cage induction motor is very good when compared to slip ring induction motor. So because of this, at running conditions, whatever the for the same ratings, the speed with respect to induction motor is very good. With respect to squirrel cage induction motor is very good when compared to slip ring induction motor or wound rotor. So this is a very important point that I am trying to tell you. So therefore, starting characteristics of the slip ring induction motor is very higher when compared to squirrel cage induction motor, whereas the running characteristics of the squirrel cage induction motor is better than the slip ring induction motor. So therefore, at the same ratings, definitely we can say that the squirrel cage induction motor has the better speed, more speed when compared to slip ring induction motor. The following performance characteristics are attributed to a 3-phase squirrel cage induction motor without screw or lower magnetizing current compared to a slip ring motor: high efficiency, high power factor, possible clogging and crawling. If you give 3-phase supply to stator of induction motor, the RMF rotates with 1.5 FM 5 magnitude. This is I will give you here. Basically, the following performance characteristics are attributed to a 3-phase squirrel cage induction motor without screwing or lower magnetizing current. So we need Without screwing, basically we need lower magnetizing current compared to a slip ring motor. High efficiency, very high efficiency, high power factor, possible cogging and crawling. So what I am trying to say is basically I am going to compare the squirrel cage induction motor and the slip ring induction motor. So if you are not going to do any screwing, definitely we need lower magnetizing currents, and also the efficiency is very higher and higher power factor, and the possible cogging and crawling are going to happen. In this, if you go for screwing, yes, there is no cogging and crawling. If you are not screwing, means definitely possible cogging and crawling are going to get effect. And also, if you go for screwing, I already told you, with the help of screwing, the efficiency decreases. So without screwing, higher efficiency. So with screwing, the power factor also decreases. So without screwing, high power factor. And with screwing, we require more amount of magnetizing current. So without screwing, we need lower magnetizing current. So these are the things which I am trying to tell you. So if you are not screwing the rotor slots in a squirrel cage induction motor, we can say that it requires. Then if you are not screwing, means basically cogging and crawling are going to present. So higher efficiency, higher power factor, and also lower magnetizing current. Or if you go for screwing, I have already told you, suppose if you are going to do the screwing in the rotor slots of a squirrel cage induction motor, cogging and crawling are absent, and also the efficiency is also very less. These things I have already told you, and also the power factor is also less, and the magnetizing current is very higher. So these are the things will happen if you go for the screwing. So without screwing means yes, crawling and cogging are present, higher efficiency, higher power factor, and also lower magnetizing current. So these are the things that you always have to keep in your mind. So if you give three-phase supply to stator of induction motor, the RMF rotates with a peak value of 1.5 Φm. I have already told you, if Φm is the peak value of a supply flux, then the RMF is going to rotate with a peak value of 1.5 Φm for a three-phase. Suppose for n phase, which is n by 2 into Φm, where n is always greater than or equal to 2 for n phase system. N is called as for n phase system. For n phase system, definitely the peak value of the RMF is nothing but n by 2 into Φm, where n is greater than or equal to 2. So this is the formula that you always have to remember. In single phase induction motor, initial push is required for rotor to move in any direction. This behavior was explained by Ferrari through double revolving field theory. I have already told you detailed explanation of the double revolving field theory, which was explained by the Ferrari. See, basically in a single phase induction motor, it is not a self-starting. So you have to give some initial push, either clockwise or anti-clockwise. Based on that, it is going to rotate. If you give an anti-clockwise push, it is going to always rotate in the anti-clockwise. Otherwise, if you give clockwise push, it will always rotate in the clockwise. So this is basic function of single phase induction motor. But I already told you, suppose if you want to make a starting, then you have to go for the auxiliary winding or the starting winding. You have to connect in parallel with the main winding. These things I have already told you. So therefore, what I am trying to say finally is basically single phase induction motor is it's not self-starting. If you want to go for starting, definitely you have to keep an auxiliary winding or starting winding. So in a single phase induction motor, the initial push is required for rotor to move in any direction, either clockwise or anti-clockwise. This behavior was explained by the Ferrari through double revolving field theory. RMF is possible with single phase, two phase and three phase winding. See, with n phase we can produce the RMF. I have already told you, for three phase also we can produce RMF, with two phase also we can produce RMF, and also with single phase also we can produce RMF. But single phase means initially we are going to operate the motor like a two phase, then after that we are going to operate like a single phase. Listen carefully. For a single phase induction motor, for starting purpose we are going to operate like a two phase, but after that, after reaching certain speed, we are going to remove the auxiliary winding. So now it is going to act like a purely single phase induction motor. So RMF is possible with single phase, two phase and three phase. But particularly we can say single phase, initially the motor is going to act like a two phase. So this is the important point that you always have to remember. Test the machine to figure out the efficiency by direct testing and also the indirect testing. So by two methods, whether you directly correct the load or indirectly means we are going to find the constant losses. So based on that, we can figure out the efficiency at any given load. So therefore, we basically test the machine to figure out the efficiency by two methods. One is called direct testing and the other is called as the indirect testing. Indirect means we are not going to correct any load directly, but we are going to find the losses based on this. Because the constant losses are same with respect of the load, so based on this we can figure out the efficiency at any given load condition. So therefore, direct testing is preferred for small machines, because for small machines we can correct the load directly and then we can figure out the efficiency. Whereas in indirect testing, we measure loss and from that we can find the efficiency. Example is swim-on test. I already told you. Suppose indirect testing means simply here basically we can't, because for a huge amount of very large machines we cannot connect the rated loads because the loads are very higher. We can't connect that load practically to that machine. So by this indirect test we are going to figure out the losses. So based on these losses are same for either irrespective of the load, the losses are always same. So based on this we can figure out the efficiency at any given load condition. So best example is called as a swim-on test. Basically it is a no load test where then we are going to find the constant losses. So based on that we can find the efficiency of any load condition. So these are the two methods by which we can find the efficiency of a machine. So direct testing is always preferred for a low rating machines and the indirect test is always preferred for the high rating machines. So take shunt motor or compound motor in a swim-on test at no load, output is always equal to 0 because here we are not going to keep any load. So IA is equal to 0, so EB into IA is always equal to 0. So therefore the output power is also equal to 0 and the full input is went into losses. I already told you the swim-on test is a no load test. At no load, whatever the current drawn is very less. So EV into IA is nearly equal to 0. So output power is equal to 0. So output, there is no useful work, or you can say there is no useful work done. So output is equal to 0. So whatever the input power accepting at this condition is equal to losses. So therefore, with the help of this we can find the losses. Then with the help of this we can find the efficiency at any condition, at any load condition. So always at swim-on test is a no load test. So shunt motors and compound motors are useful. But we cannot do the DC series motor at no load because you cannot use the DC series motor for the swim-on test because it's a no load test. Definitely then we go for the field test for finding the efficiency for the DC series motors. So take shunt motor or compound motor in a swim-on test at no load and output is equal to 0 and full input is went into losses. So what I'm trying to say finally is basically DC series motor is at no load we can't operate it, so we can't do the swim-on test. So if we want to find the efficiency of DC motor or DC generator, we have to use the field test. So the different types of motors are available. They are basically split phase or resistance split phase, capacitor start and capacitor start and capacitor run, or permanent capacitor or capacitor run. Sure, serial pole motor. So these are the different types of single phase induction motors which are available in electrical machines. So therefore, the different types of motors which are available, they are called as the split phase or resistance split phase, capacitor start and the capacitor start and capacitor run. It is also called as the permanent capacitor or capacitor run. And similarly, there is another thing which is called as the shaded pole motor. So these are the different types of single phase induction motors which are available in the electrical machine subject. So listen carefully. The different types of motors which are available, they are basically split phase or the resistance split phase, capacitor start and capacitor run is also called as the permanent capacitor or capacitor run, and the shaded pole motor. So these are the different single phase induction motors which are available. So for these motors, definitely we can say that the starting torque is not equal to 0. So while starting, the starting torque is not equal to 0, we can say these are said to be self-starting single phase induction motors. The different types of motors which are available, they are called as the split phase or the resistance split phase, capacitor start and capacitor run is also called as a permanent capacitor or capacitor run, and the shaded pole motor. Capacitor start is available. So capacitor start is available with large ratings, so it is highly costly. Shaded pole motor is very cheap and the percentage of efficiency is less than 50% and highly popular. So if you compare the capacitor start and the shaded pole, see out of all the single phase induction motors, see the capacitor start is available with large ratings, so it is highly costly. So therefore, whatever the capacitor start you are going to get, it is basically said to be highly costly and it is always available with the larger ratings. Whereas the shaded pole motor is a very cheap one, and also the percentage of efficiency is very less, and also it is very highly popular among the remaining single phase induction motors. And I have already told you the starting torque of the single phase, the starting torque of the shaded pole motor is very less when compared to remaining single phase induction motors. Also I have already told you, always in a shaded pole motor, the rotor is going to rotate from the unshaded part to the shaded part. These things I have already told you, and I have already told you that whatever the flux in the non-shaded is always going to lead the flux in the shaded, because whatever the flux in the shaded is always going to lag the flux in the unshaded pole. I've already told you all these crazy things in the shaded pole itself. So therefore, capacitor start is always available with the larger rating, so it is highly costly, and the shaded pole motor is very cheap, and the percentage of efficiency is less than 50%, and it is very highly popular remaining all the single phase induction motors. So whatever the capacitor start, single phase induction motor is always available with the larger ratings, so it is highly costly, whereas the shaded pole motor is very cheap and the percentage of efficiency is very less, and it is less than even 50%, and it is highly popular when compared to remaining single phase induction motors. When a single phase induction motor is excited with a single phase AC voltage, the magnetic field setup is equivalent to two fields rotating at synchronous speed in the opposite direction. So when a single phase induction motor is excited with a single phase supply, the magnetic field setup is equivalent to two fields rotating at synchronous speed in opposite directions. I have already told you, for a pure single phase induction motor, if you give a AC supply, definitely there are two fields, two RMFs are going to rotate in the opposite direction. One is called as the forward RMF and the other is called as a negative or backward RMF. So that is the reason at starting the net torque is equal to 0. So therefore it is not a self-starting induction motor. That is the reason we go for the auxiliary winding or the starting winding. We are going to connect in parallel with the main winding to make it a self-starting. So this is the crazy thing that I have already told you in the single phase induction motor. So when a single phase induction motor is excited with a single phase AC supply, the magnetic field setup is equivalent to two fields rotating at synchronous speed in the opposite direction. This concept is called as a double field revolving theory, which was explained by the Ferrari. A single phase induction motor is not self-starting as such, because a single phase induction motor develops only pulsating magnetic field which provides zero torque at the standstill. I have already told you, single phase induction motor is not a self-starting induction motor. So therefore, because at the starting, whatever the torque in the forward torque is equal to backward torque, so net torque is equal to 0. These things I have already told you in the induction motor concept only. That is the reason it is not a self-starting. So if you want to give a starting, you have to manually give the rotation either clockwise or anti-clockwise. So based on the direction you are giving, it is going to rotate as per the convenience, as per the direction that you have rotated. But this is a very severe pain in the neck. So we go for the extra winding, which is called as the auxiliary winding or the starting winding. So with the help of this, now we can provide the non-zero starting torque at the starting condition itself. So therefore we can say that a single phase induction motor is not self-starting as such, because a single phase induction motor develops only pulsating magnetic field which provides a zero torque at the standstill condition. The capacitor start single phase induction motor develops much larger starting torque in comparison with the split phase motor, because the use of capacitors in the auxiliary winding enables the torque. The capacitor start single phase induction motor develops much larger starting torque in comparison with the split phase motor, because the use of capacitors in the auxiliary winding increases the torque or enables the torque. I have already told you, with the help of capacitor, we are going to increase the phase angle between the auxiliary winding current and the main winding current. So whenever the alpha increases, alpha is called as a phase angle between the main winding and the auxiliary winding current. So whenever alpha increases, I have already told you, the starting torque is directly proportional to main winding current into auxiliary winding current into sine of alpha. As alpha increases, sine alpha increases, the starting torque is also increases. So therefore, whatever the starting torque in the capacitor start is always higher when compared to split phase motor. So therefore, the capacitor start single phase induction motor develops much larger starting torque in comparison with the split phase motor, because the use of capacitors in the auxiliary winding increases the torque or enables the torque. The capacitor start single phase induction motor develops much larger starting torque in comparison with the split phase motor, because the use of capacitors in the auxiliary winding enables the torque or increases the torque. So we can say simply that whatever the capacitor start single phase induction motor develops much larger starting torque in comparison with the split phase motor, because the use of capacitors in the auxiliary winding is going to increase the torque or enables the torque. This concept I have already told you. Characteristics in general to get a shape to give a large starting torque. So what are the slip characteristics in general to get a shape to give a large starting torque? So what are the slip characteristics in general to get a shape to give a large starting torque? Always the slip characteristics in general to get a shape to give a large starting torque. A ceiling fan fails to start because of the following reasons. See, a ceiling fan fails to start because of the following reasons. See, main winding is open circuited. If the main winding is open circuited, IM is equal to 0, the starting current, the starting torque is equal to 0. Auxiliary winding is open circuited, then IA is equal to 0, again starting torque is equal to 0. Capacitor is short circuited. Whenever the capacitor is short circuited, whatever the alpha between the IM and IA is very less. So starting torque is also very less. So this is not able to enough required to start the rotor. So therefore, a ceiling fan fails to start because of the following reasons. I have already told you the starting torque is directly proportional to main winding current into auxiliary winding current into sine of alpha. Alpha is the phase angle between the main winding current and the auxiliary winding current. So whenever the main winding is open circuited, IM is equal to 0, so starting torque is equal to 0. Auxiliary winding is open circuited means IA is equal to 0. Again, starting torque is equal to 0. Capacitor is short circuited means the alpha between the IM and IA is very less. So this is not enough to even it is not even enough to rotate the rotor. So these are the conditions by which we can say a capacitor, a ceiling fan fails to rotate. A single phase capacitor start induction motor, the direction of rotation can be changed by reversing the main winding terminals or auxiliary winding terminals, but not both. See, if you want to change the rotation of the rotor of a single phase induction motor, you have to interchange the terminals of the main winding or you have to change the terminals of the auxiliary winding. You have to change any one, not both. If you change both, again it will be rotating in the same direction because the starting torque is directly proportional to IM into IA into sine alpha. If both are negative to negative is again positive. That is the reason you have to change only either of one terminals only you have to interchange. So for a single phase capacitor start induction motor, the direction of rotation can be changed by reversing the main winding terminals or auxiliary windings, but not both. For a single phase capacitor start induction motor, the direction of rotation can be changed by reversing the main winding terminals or auxiliary winding terminals, but not both. The centrifugal switch used in a single phase induction motor is to cut off the starting winding at an appropriate instant. I have already told you whatever the centrifugal switch is basically a speed sensitive centrifugal switch. So based on the speed, whenever the speed is reaching around 70 to 80% of the rated speed, then at that time the centrifugal switch should operate and it should open circuit, it should remove the starting winding or the auxiliary winding from the circuit. So therefore, now it is going to act like a purely single phase induction motor. So the centrifugal switch used in a single phase induction motor is to cut off the starting winding at an appropriate instant. So whatever the centrifugal switch is basically speed sensitive centrifugal switch. So whenever the rotor speed is reaching around 70 to 80%, then the switch should operate and it should remove that starting winding or the auxiliary winding from the overall circuit. So always the centrifugal switch used in a single phase induction motor is to cut off the starting winding at an appropriate instant. The magnetizing current component of the no load current of an induction motor is much larger than a corresponding transformer because of an air gap in the magnetic circuit. I already told you the magnetizing current component of the no load current of an induction motor is much larger than a corresponding transformer because of an air gap in the magnetic circuit. These things I have already told you in the concept of comparison of the transformer and also the induction motor, because in an induction motor air gap is present, so it requires huge amount of magnetizing current to produce a constant rated flux, whereas in the transformer we need, at no load condition, we need only the magnetizing current of only 2 to 5%, whereas here the no load current here in the induction motor is around 30 to 50%. So because of this, huge amount of magnetizing current is also going to get happen, and whatever the power factor angle, the power factor angle of the transformer is lesser when compared to power factor angle of the induction motor. So finally I can say that the no load current of the induction motor is very higher when compared to no load current of the transformer. Similarly, the magnetizing current of the induction motor is very higher when compared to the magnetizing current of the transformer. Similarly, the power factor angle of the induction motor is very higher when compared to the power factor angle of the transformer. It is based on no load power factor angle. So the no load power factor of induction motor is very lesser when compared to the no load power factor of the transformer. So finally I can say that the magnetizing current component of the no load current of an induction motor is much larger than a corresponding transformer because of an air gap is present in the magnetic circuit. The steady state speed of a 3-phase squirrel cage induction motor delivering a load torque depends upon the supply voltage, supply frequency, load torque, speed characteristics. These things I have already told you. Whatever the steady state speed of a three-phase squirrel cage induction motor delivering a load depends upon the supply voltage, supply frequency, load torque, speed curve. So load torque, speed characteristics. See, whatever the speed, the steady state speed of a squirrel cage induction motor delivering a load is going to depend upon the, I already told you, torque is a function of voltage and the frequency, and based on this we are going to get the speed. So therefore simply we can say that the steady state speed of a three-phase squirrel cage induction motor delivering a load depends upon the supply voltage, supply frequency, and also the load speed, torque speed characteristics. So based on these three things, finally the steady state speed of the squirrel cage induction motor is going to get decided. The steady state speed of a three-phase squirrel cage induction motor delivering a load torque depends upon the supply voltage, supply frequency, and the load torque speed characteristics. The steady state speed of a three-phase squirrel cage induction motor delivering a load torque depends upon the supply voltage, supply frequency, load torque speed characteristics. A polyphase slip ring induction machine has the stator and rotor windings wound for the same number of pairs of poles with the number of phases either equal or different. So this is a very important point that you always have to understand. A polyphase slip ring induction machine has the stator and the rotor windings wound for same number of pair of poles with the number of phases either equal or different. See, I have already told you one important condition that you always need to remember, which is the number of poles on the stator and the number of poles in the rotor should be always same. Then only the torque is going to get produced. But it is not compulsory to have the same phases. Phases can be same or different, but the poles should be always same. So this is a very basic agenda that you always have to keep in your mind. So whenever the poles are same, then the torque is going to get produced. Otherwise, torque is not at all going to get produced. But the number of phases on the stator and the rotor may be same, they may be different. It doesn't matter. So a polyphase slip ring induction machine has the stator and the rotor windings wound for the same number of pair of poles with the number of phases either equal or different. So we can say that if the number of poles should be always same on the stator and also on the rotor. But whereas the number of phases can be either same or different when compared to both stator and rotor. So finally I can say that the number of poles in the stator should be always equal to number of poles in the rotor. Then only the torque is going to get produced. But the number of phases on the stator and the number of phases on the rotor, they may be same, they may be different. While plugging a three-phase induction motor, if one supply terminals get disconnected, then the motor will continue to run in the same direction because now it acts like a single phase induction motor. I already told you, suppose while plugging a three-phase induction motor, if one supply terminal gets disconnected, then the motor will continue to run in the same direction because now it acts like a single phase induction motor. But the speed is now somewhat lesser when compared to the previous speed. So whenever the three-phase induction motor, suppose due to some fuse broken, one of the terminal got broken, then only two separate terminals are there. Now it is going to behave like a single phase induction motor. So therefore simply we can say that yes, it is going to rotate. Still it is going to rotate because already it is in the rotation. So starting torque is not at all required. Already it is in the rotation. So it is going to act like a single phase induction motor. See, I already told you, single phase induction motors are not a self-starting. Means if starting the rotor is rest, then it can't provide the initial torque. But if it is running, then it can provide the torque because it is always having the RMF. So therefore, whenever it goes slightly, either clockwise or anti-clockwise, it is always going to rotate. But here always it is rotating, but the speed will be somewhat lesser when compared to previous speed. So finally, I can say that while plugging a three-phase induction motor, if one supply terminals get disconnected, then the motor will continue to run in the same direction because now it is going to act like a single-phase induction motor. But now the speed is somewhat lesser when compared to the previous speed. So while plugging a three-phase induction motor, if one supply terminals get disconnected, then the motor will continue to run in the same direction because now it is going to act like a single-phase induction motor. In the operation of a three-phase induction motor running at full load, if one of the supply line fuses blows off, the motor will continue to run with the increased step and take excessive supply current. In the operation of a three-phase induction motor running at full load, if one of the supply line fuse blows off, the motor will continue to run with the increased slip because the speed is decreased. Whenever the speed is decreased, the slip will increase and takes excessive supply current because I have already told you it is a single phase, so it is going to draw the huge amount of current. So therefore I've already told you this with this point. So whenever a three-phase supply, so for a three-phase induction motor, if one of the fuses broken, it is going to act like a single-phase induction motor. It is going to rotate in the same direction with the speed lesser. So speed is whenever the rotor speed decreases, the slip field increases, and it is going to take a excessive current. So it is going to take a excessive current because I have already told you I2 dash is equal to S into E2 by rotor R2 square plus SX2 square. As S increases, the current also increases. So it is going to take excessive supply current. In the operation of a three-phase induction motor running at full load, if one of the supply line fuse blows off, the motor will continue to run with the increased slip and take excessive supply current. The phenomena of crawling is usually not found slip ring induction motors because these motors have high resistance rotor winding. The phenomena of crawling is usually not found in slip ring induction motors because these motors have high resistance rotor winding. I already told you crawling is nothing but, so basically what is the crawling? Crawling is the motor is going to think that whenever the rotor speed is nearly equal to ns by 7, it may think that it is a stable region, but actually it is not because of the harmonics of the flux which is present in the air gap. This is going to, the main reason for this one is because of the slots. The slots in the stator and the rotor is going to distort the flux in the air gap. So because of this non-circular flux, we are going to get the harmonics. In that, the seventh harmonic is more dominant. So rotor may think that it is a stable region. So overall torque with respect to speed characteristics are going to get changed. And whenever NR is nearly equal to ns by 7, the induction motor may think that it is said to be stable region and is going to operate at that speed for permanently. So this crawling is going to happen only in the case of squeeze cage induction motor, but not in the case of slip ring induction motor because at starting it has a huge amount of starting torque. We can say it is going to have huge amount of rotor winding resistance. So because of this, the crawling will never happen in the slip ring induction motors. The phenomenon of crawling is usually not found in slip ring induction motors because these motors have the high resistance rotor windings. The phenomenon of crawling is usually not found in slip ring induction motors because these motors have the high resistance rotor winding. In a three-phase induction motor, if the angular speed of the stator field is omega and the actual speed of the rotor is omega r, and the stator induced EMF is given by Es is equal to N1 into omega into kWs into phi into sin omega t, where N1 being the stator turns per phase, then the rotor EMF with N2 as the rotor per turns per phase will be kWs is called as the stator winding factor and kWr is called as a rotor winding factor, which is equal to R is equal to N2 into omega minus omega r into kWr into phi into sin of omega minus omega r into t. In a three-phase induction motor, if the angular speed of the stator field is W and the omega and the actual angular speed of the rotor is omega r, and the stator induced EMF is given by Es is equal to N1 into omega into kWs into phi into sin omega t, where N1 be the stator turns per phase, then the rotor EMF with N2 as the rotor turns per phase will be kWs is called as the stator winding factor and kWr is called as the rotor winding factor is equal to, here ER is equal to the number of turns of rotor, the number of rotor turns per phase is N2 into the relative speed is omega minus omega r into kWr into phi into sin of the relative speed difference omega minus omega r into t. So always N2 is the number of rotor turns per phase, the speed difference omega minus omega r into k omega r into phi into sin of omega minus omega r into t. So always there is a phase difference, the relative speed difference we have to take the factor. So simply the relative speed difference we have to take, which is N2 into omega minus omega r into kWr into phi into sin of omega minus omega r into t. In a three-phase induction motor, if the angular speed of the stator field is omega and the actual angular speed of the rotor is omega r, and the stator induced EMF is given by Es is equal to N1 into omega into kWs into phi into sin omega t, where N1 being the stator turns per phase, then the rotor EMF with N2 as the rotor turns per phase will be kWs is called as the stator winding factor and kWr is called as the rotor winding factor. So ER is equal to N2 into omega minus omega r into kWr into phi into sin of omega minus omega r into t. So we have replaced N1 by N2, omega by omega minus omega r, and kWs by kWr, and phi is same, sin of here omega minus omega r into t. So this is the equation, EMF induced in the rotor per phase, this is the equation. So torque is directly proportional to S into V square. I already told you in a stable region, the basic equation is torque is directly proportional to S into V square by R2 into F. if you assume R2 and Fs constant, so we can use torque is directly proportional to S into P square. If a three-phase induction motor and a single-phase induction motor of the same kilowatt rating and same winding voltage are compared, then the three-phase induction motor will be smaller in size and more efficient than a single-phase induction motor. See, I have already told you, three-phase induction motor will be smaller in size and more efficient when compared to single-phase induction motor. So this is the important point that you always need to understand. A three-phase induction motor will be always smaller in size and more efficient when compared to single-phase induction motor. That is the reason in all the industrial purpose we are going to use a three-phase rather than a single-phase induction motor. So if a three-phase induction motor and a single-phase induction motor of the same kilowatt rating and the same winding voltage are compared, then the three-phase induction motor will be smaller in size and more efficient than a single-phase induction motor. So I have already told you, if you compare the three-phase and the single-phase, always three-phase is smaller in size and more efficient when compared to a single-phase induction motor. So I have already told you, if a three-phase induction motor and a single-phase induction motor of the same kilowatt rating and same winding voltage are compared, then definitely a three-phase induction motor will be smaller in size and more efficient than a single-phase induction motor. So basically, if you take a three-phase induction motor and a single-phase induction motor of same kilowatt rating and same winding voltage, then definitely we can say that the three-phase induction motor will be smaller in size and more efficient when compared to single-phase induction motor. So a smaller air gap in a polyphase induction motor helps to reduce the magnetizing current. And what I told you, basically, smaller the air gap means less magnetizing current is required to bring back the rated flux in the air gap. So more is the air gap means we need to bring more amount of magnetizing current. So less is the air gap means we need less amount of magnetizing current to produce a rated flux in the air gap. So this is a very important one that you always need to understand. So when the air gap is increased in induction motor, then a spot factor will reduce. I have already told you, whenever you increase the air gap, definitely the magnetizing current component will increase. So whenever the magnetizing current component increases, definitely the power factor, the no load power factor angle increases. So power factor will reduce. So therefore, simply we can say that when the air gap is increased in an induction motor, we can say that the IM increases, so I naught increases, so phi naught increases, so cos of phi naught will decrease. So whenever the air gap is increased in the induction motor, then its power factor, the no load power factor will reduce. In no load test of induction motor is core loss plus friction loss and windage losses. See, in a no load test of induction motor is core loss plus friction loss and the windage loss. I have already told you, no load test in an induction motor is similar to open circuit test of a transformer. In a no load test, so in no load test of induction motor, I have already told you, NR is nearly equal to NS. So slip is equal to nothing but slip is equal to 0 because NR is nearly equal to NS. So whenever slip is equal to 0, the torque is equal to 0. When torque is equal to 0, the output, you can say that the output power is also equal to 0 because P is equal to T into omega. As slip is equal to 0, torque is equal to 0. As torque is equal to 0, output power is equal to 0. So there is no useful output power. So whatever the input is in the terms of losses. So whatever the losses, it is equal to the no load input is equal to losses. Whatever the input is based in the terms of losses, the losses are the core losses plus the friction and windage losses. It is also called as the mechanical losses. So these are the only two losses that are going to get occur. So core loss plus the mechanical losses also called as the friction and the windage losses. See, I have already told you in the stable region, torque is directly proportional to S into V square by R2 into F. If I assume V is a constant and F is a constant, definitely I am going to get torque is proportional to S by R2. So from no load to full load, the speed of induction motor is nearly equal to NS. I have already told you, see, it was lesser than NS, but it will be not a huge difference. The difference is very less. So whatever the difference between the NR and NS is very less. It is not a huge value. So therefore, from no load to full load, yes, the speed will reduce, but whatever the speed reduce, the difference is somewhat lesser. So therefore, from no load to full load, the speed of induction motor is nearly equal to NS, but not exactly. So it is nearly equal to NS. So unbalanced supply produces negative sequence components then slip is equal to ns plus n by ns. So f dash is equal to s into f currents induced in the rotor. I've already told you, see, unbalanced supply means we can go for the positive sequence, negative sequence and zero sequence. So negative sequence are always of opposite direction. So therefore, now ns and nr both are quite opposite because of this negative sequence. So ns, the relative speed, now both are in this opposite direction. So the relative speed is ns plus nr. So slip is equal to ns plus nr by ns. So whatever the frequency is nothing but f dash is equal to s into f. So this is the frequency of the induced currents in the rotors because of this negative sequence harmonics. So we can say that f dash is equal to s into f. So this is the frequency of the harmonics which are induced in the rotor because of this negative sequence harmonics. So f dash is equal to s into f. So this is the frequency of the current induced in the rotor because of this unbalanced supply, or simply we can say negative sequence harmonics. So unbalanced supply produces negative sequence harmonics. Then slip is equal to ns plus nr by ns. So f dash is equal to s into f. So this is the frequency of the current which are induced in the rotor because of this negative sequence harmonics. But the effect on R1, R2, X1, X2, Xm on increasing the air gap of induction motor. So now we will discuss what is the effect on the R1, R2, X1, X2, Xm on increasing the air gap of the induction motor. See, R1 is same, the resistance is always same, R2 is also same, these are independent of the air gap. So R1 is same and R2 is same. So now we will see X1, X2 and Xm. See, X1 is nothing but X1, whenever you increase the air gap, definitely the leakage flux increases. So therefore, the X1 increases. Similarly, the leakage flux also increases of the rotor, so X2 also increases. Then definitely, we can say Im. Im is nothing but magnetizing current. Whenever the air gap increases, the magnetizing current is also increases. Then what is the value of Xm? Xm is equal to V by Im. As a V is a constant, but I am increasing the Im, so Xm will reduce. So this is the point that you always need to remember. So the effects on R1, R2, X1, X2, Xm on increasing the air gap of induction motor. R1 and R2 are same, but whenever the air gap increases, the leakage flux, the stator leakage flux increases, so X1 increases. The rotor leakage flux increases, so X2 increases. Whereas Im, the magnetizing current also increases. I've already told you Im is nothing but V by Xm. So our Xm is equal to V by Im. As Im increases, Xm decreases. So therefore we can say whenever the air gap increases, R1 is same, R2 is same, X1 increases, X2 increases, whereas Xm will decrease. So these are the effects on these parameters while increasing the air gap of the induction motor. Say I've already told you in the V by F control, the slip at maximum torque is equal to R2 by X2. As the frequency increases, then X2 increases, then the slip at maximum torque will decrease. Simply because we can say slip is inversely proportional to frequency and is also inversely proportional to ns, because I've already told you F is nothing but is proportional to ns because ns is proportional to F. So simply we can say that as the frequency increases, the ns increases, but slip at maximum torque will reduce. So finally I can say that as the frequency increases, the slip at maximum torque will reduce, as the synchronous speed will increase. So V by F control is also called as a constant V by F. For a constant V by F, I have already told you the maximum torque is always same. But if you want the same torque, definitely the slip speed should be always equal. In a V by F control, if you want the torque to be same, then definitely the slip speed should be always same, which is S1 into NS1 is equal to S2 into NS2, or simply NS1 minus NR1 is equal to NS2 minus NR2. So these things I have already told you in detail regarding the V by F control itself.